In segment 1.1, we're going to talk about cryptographic hash functions. We'll talk about what they are and what their properties are. And then later we'll move on and talk about what their applications are. So a cryptographic hash function is a mathematical function, and it has three attributes that we need to start with. First of all, a hash function can take any string as input, absolutely any string of any size. It produces a fixed size output. We'll use 256 bits in this series of lectures because that's what Bitcoin does. And it has to be efficiently computable, meaning given a string, in a reasonable length of time, you can figure out what the output is. So that's a hash function, but we're going to need hash functions that are cryptographically secure. The cryptographic properties of hash functions are a complicated topic in general, but we're going to focus here on three particular properties, and I'll explain in a minute what those are. In particular, that the function is collision-free, that it has a hiding property, and that it's puzzle-friendly. And for each of these, I'll talk about what the property is, what it means, and then I'll talk about why it's useful to have a function that has that property. So first, collision-free. So the first property that we need from a cryptographic hash function is that it's collision-free. And what that means is that it's impossible, nobody can find values x and y such that x and y are different, and yet the hash of x is equal to the hash of y. And so if we look at the operation of the function as depicted by one of these red arrows, here's x and h of x, and here's y and h of y, then nobody can find a situation like this, that you have an x and y that are separate, and yet when you hash them, they hash to the same value. Now, one thing to notice is that I said nobody can find. I didn't say that there is no collision. Because if you think about it, there has to be a collision. Collisions do exist, and to understand why that is, we can use this diagram. Over here on the left, I'm depicting all of the possible inputs to this function, which can be a string of any size. And over here, I have all of the possible outputs, which has to be a string of 256 bits in size. So the right-hand side here, the outputs, there are only 2 to the 256 possibilities. Over here, there are more possibilities. And so if you think that every point over here on the left is going to be mapped by an arrow to some point on the right, you can see that as you go from all the points over here on the left into the right, it has to get crowded, and in fact, that there have to be multiple values over here on the left that map to the same output over here. In fact, in general, there will be a very large number of possible inputs that map to any particular output. So collisions do exist. I said before, nobody can find a collision, and that's the key question. We know collisions exist. The question is, are there any collisions that are findable by regular people using regular computers? Okay. Now, to make things even worse, I said that it has to be impossible to find a collision. Let me tell you how to find a collision, because there's a method that's guaranteed to work. And the method works like this, that we're going to pick 2 to the 130 randomly chosen inputs over on the left cloud of that previous diagram. And if we pick those 2 to the 130 randomly chosen inputs, it turns out there's a 99.8% chance that at least 2 of them are going to collide. And so this is a very simple method for finding a collision. It works no matter what the hash function is, but of course the problem is that this takes a very, very long time to do. You have to compute the hash function 2 to the 130 times, and that's of course an astronomical number. This method works no matter which hash function we're using. There's still a 99.8% probability that this works, and if it doesn't work, just try it again. It'll probably work the next time. But this doesn't really matter, and the reason it doesn't really matter is that this procedure takes 2 to the 130 steps in order to get to that high probability. So we can say something like this. We can say that if every computer ever made by humanity was computing since the beginning of the entire universe up to now, the odds that they would have found a collision is still infinitesimally small. So small that it's way less than the odds that the Earth will be destroyed by a giant meteor in the next 2 seconds, which didn't happen. Okay, so we know how to find a collision, but this method takes too long to matter. The question is there some other method that could be used on a particular hash function in order to find a collision? And that's the question that is harder to answer. Is there a faster way to find collisions? Well, for some possible values of hash functions, of course there are. For example, if our hash function were to simply take the input modulo 2 to the 256, that is, it just selected the last 256 bits of the input, then we would know an easy way to find a collision. One collision would be the values 3 and 3 plus 2 to the 256. So for some possible values of the hash function, it's very easy to find a collision. For others, we don't know. Now, one thing I need to note is that there's no hash function in existence which has been proven to be collision-free. There are just some that people have tried really, really hard to find collisions and haven't succeeded. And so we choose to believe that those are collision-free. Okay. Now, what good does collision freedom do us? If we can assume that we have a hash function that is collision-free, then we can use that hash function as a message digest. And what I mean by that is the following, that if we know that x and y have the same hash, then it's safe to assume that x and y are the same. Because if someone knew an x and y that were different that had the same hash, of course that would be a collision. Since there's not a collision that we know of, then knowing the hashes are the same, we can assume that the values are the same. And this lets us use the hash as a kind of message digest. Suppose, for example, that we had a file, a really big file, and we wanted to be able to recognize later whether another file was the same as the file we saw the first time. Right? So one way to do that would be to save the whole big file, and then when we saw another file later, just compare them. But because we have hashes that we believe are collision-free, it's more efficient to just remember the hash of the original file. Then if someone shows us a new file and claims that it's the same, we can compute the hash of that new file and compare the hashes. If the hashes are the same, then we conclude that the files must have been the same. And that gives us a very efficient way to remember things we've seen before and recognize them again. And of course, this is useful because the hash is small. It's only 256 bits, while the original file might be really big. So hash is useful as a message digest, and we'll see later on in this lecture and in subsequent lectures why it's useful to use hashes as message digests. So the second property that we want from our hash function is that it's hiding. And the property that we want is something like this, that if we're given the output of the hash function, that there's no feasible way to figure out what the input x was. The problem is that this property doesn't exactly hold. And to understand why that's the case, let's look at this example. So here, what we're going to do is an experiment where we flip a coin, and if the result of the coin flip was heads, we're going to return the hash of the string heads, and if the result was tails, we're going to return the hash of the string tails. And now we're going to ask someone who didn't see the coin flip but only saw this hash output to figure out what the string was that was hashed. That, of course, is going to be easy. It's easy in this scenario to find what the input string was. It's easy to find x. You simply compute the hash of the string heads and the hash of the string tails, and you see which one you got. And so in just a couple of steps, you can figure out what x was. So the reason this example failed, that is the reason why an adversary was able to guess what the string was that there were only a couple of possible values of x. And so if we're going to have a hiding property like this, it needs to be the case that there's no value of x which is particularly likely. That is, x has to be chosen from a set that's in some sense very spread out, so that this method for the adversary of just trying all the possible values of x, or just trying a few values of x that are especially likely, is not going to work. So the hiding property that we are going to need to set up is a little bit more complicated. And the way we're going to fix this problem with the common value x, like heads and tails, is we're going to take the x and we're going to put next to it, we're going to concatenate with it a value r, which is chosen from a distribution that's really spread out. And so this h of r concatenated with x, that means take all the bits of r and put after them all the bits of x. And so what we're going to say is, given the hash of r together with x, that it's infeasible to find x, and that this will be true in the formally stated property that if r is a random value chosen from a distribution that has high min entropy, then given the hash of r concatenated with x, it's infeasible to find x. And what does high min entropy mean? Well, it captures this intuitive idea that r is chosen from a distribution that's really spread out. And what that means specifically is that there's no particular value that r could have had that would occur with more than a negligible probability. So for example, if r is chosen uniformly from among all of the strings that are 256 bits long, then any particular string was chosen with probability 1 in 2 to the 256, which is truly a negligible value. So as long as r was chosen that way, then the hash of r concatenated with x is going to hide x. And that's the hiding property that the hash function will be deemed to have. Okay, now let's look at an application of that hiding property. And in particular, what we want to do is something called a commitment. And this is kind of the digital analogy of taking a value, a number, and sealing it in an envelope and putting that envelope out on the table where everyone can see it. Now, when you do that, you've committed to what's in the envelope, but you haven't opened it. It's secret from everyone else. Later, you can open the envelope and get out the value, but it's sealed. So commit to a value and reveal it later. We want to do that in a digital sense. So to be more specific about what is the API that we're going to provide here, the commitment API looks like this, that there are two things you can do. First, you can commit to a message, and that's going to return two values, a commitment and a key. Think of the commitment as the envelope that you're going to put on the table, and the key as a secret key for unlocking the envelope. Then later, you allow someone else to verify, given a commitment and given a key, which you've told them in the meantime, and the message, they can verify that that commitment, key, and message really do go together, and this will return a true or false. Okay, now to seal MSG in an envelope, what we do is we commit to the message, and that returns a commitment and a key, and then we publish the commitment. That's putting the envelope on the table. Now later, to open the envelope, what we're going to do is publish the key and the message that we committed to, and then anybody can use this verify call with the commitment that we published previously, the key and message that we just announced, to check the validity of our opening the envelope. Okay. And the property, of course, we want from this is that it behaves like sealing an envelope. And in particular, the two security properties are these. First, given COM, the commitment, the envelope on the table, that someone just looking at the envelope can't figure out what the message is. The second property is that it's binding, that when you commit to what's in the envelope, you can't change your mind later. That is, it's infeasible to find two different messages such that you can commit to one message and then later claim that you committed to another, and the whole thing will verify. Okay, so how do we know that these two properties hold? Well, first we need to talk about how we're going to actually implement commitments. And the way we're going to implement commitments is like this. That in order to commit to a value message, we're going to generate a random 256-bit value and call it the key. And then we're going to, as the commitment, return the hash of the key concatenated together with the message. And as the key value, we're going to return h of this key. And then later, to verify, someone is going to compute this same hash of the key they were given, concatenated with the message, and they're going to check whether that's equal to the commitment that they saw. Okay, so this is a way of using hash functions both in the commitment and in the verification. So now the security properties, if we go down to the security properties that were at the bottom of the previous slide, and we just plug in the definitions of how we're going to implement this here, that is, this used to say COM, given COM, infeasible defined message, we just plug in what COM is. COM is the hash of key concatenated with message. And similarly down here, this is what happens when we take what was written there before and plug in the definition of verify in COM. Okay, so now what these properties become, the first one is given h of key concatenated with message, it's infeasible to find message. Well, it turns out that that's exactly the hiding property that we talked about before. Key was chosen as a random 256-bit value, and therefore the hiding property says that if we take the message and we put before it something that was chosen from a very spread out distribution, like I said, a random 256-bit value, then it's infeasible to find the message. So this is exactly the hiding property. And this one down here turns out to be exactly the collision-free property. So that if someone can find two messages which have the same hash like this, well, then they have an input value here and an input value there that are different, and yet those have the same hash. And so because of the two security properties we've talked about for hashes so far, this commitment scheme will work in the sense that it will have the necessary security properties. Okay, so that's the second security property of hashes, that they're hiding, and the application of that is commitments. The third security property we're going to need is that they're puzzle friendly. And this is, again, a little bit more complicated, but let me just go through it a bit by bit. That for any possible output value y that you might want from the hash function, we're going to use y as an output value of the hash later, that if k is chosen from a distribution that has high min entropy, that is, k is chosen randomly from some set that's super spread out, then there's no way to find an x such that the hash of k and x is equal to y. So what this means is basically that if someone wants to target the hash function, if they want it to come out to some particular output value y, that if there's part of the input that is chosen in a suitably randomized way that it's very difficult to find another value that hits exactly that target. So the application we're going to use of this is we're going to build a search puzzle. And what that means is we're going to build a mathematical problem which requires searching a very large space in order to find the solution, and where there's no shortcuts, a way to find a good solution other than searching that large space. That's a search puzzle. To be more specific, the idea is that if we're given a puzzle ID, which is chosen from some high min entropy distribution, that is some very spread out probability distribution, and we're given a target set Y, which someone wants to make the hash function fall into, then we want to try to find a solution X, so that if we hash the puzzle ID together with the solution X, we get a result that's in the set Y. So the idea is Y is a target range or set of hash results that we want. ID specifies a particular puzzle, and X is a solution to the puzzle. And the puzzle-friendly property here implies that there's no solving strategy for this puzzle, which is much better than just trying random values of X. And so if we want to pose a puzzle that's difficult to solve, that we can do it this way, as long as we can generate puzzle IDs in a suitably random way. And we're going to use that later when we talk about Bitcoin mining. That's the sort of computational puzzle we're going to use. Okay, so we've talked about 3 properties of hash functions and 1 application of each of those. Now let me talk just very briefly about the particular hash function we're going to use. There are lots of hash functions in existence, but this is the one Bitcoin uses, and it's a pretty good one to use. It's called SHA-256, or SHA-256, and it works like this. Basically, it takes the message that you're hashing, and it breaks it up into blocks that are 512 bits in size. The message isn't going to be, in general, necessarily exactly a multiple of the block size, so we're going to add some padding at the end. And the padding is going to consist of, at the end of the padding, a 64-bit length field, which is the length of the message in bits. And then before that, it's going to consist of a 1-bit, followed by some number of 0 bits. And you choose the number of 0 bits so that this comes out exactly to the end of a block. So once you've padded the message so that its length is exactly a multiple of the 512-bit block size, you then chop it up into blocks, and you then execute this computation. You start with a 256-bit value called the IV. That's just a number that you look up in a standards document. And then you take the IV and the first block of the message. You take those 768 total bits, and you run them through this special function C. The compression function, and out comes 256 bits. You now take that with the next 512 bits of the message, run it through C again, and you keep going. Each iteration of C crunches in another 512-bit block of the message and mixes it in sort of logically to the result. And when you get to the very end, you have consumed all of the blocks of the message plus the padding. The result is the hash. That's a 256-bit value. And it's easy to show that if this function C, this compression function, is collision-free, then this entire hash function will also be collision-free. The other properties are a little bit more complicated, so I won't talk about them here. Okay, so we've talked about hash functions. We've talked about what hash functions do. We've talked about 3 properties of hash functions and applications of those properties, and the specific hash function that we use in Bitcoin. In the next lecture segment, we'll talk about ways of using hash functions to build more complicated data structures that are used in distributed systems like Bitcoin. In section 1.2, we're going to talk about hash pointers and their application. A hash pointer is a kind of data structure that turns out to be used a lot in the systems that we're talking about. And a hash pointer is basically a simple thing that we're going to take a pointer to where some information is stored, and we're going to, together with that pointer, store a cryptographic hash of the information. So whereas a regular pointer gives you a way to retrieve the information, a hash pointer is going to let us ask to get the information back. And it's also going to let us verify that the information hasn't changed. So a hash pointer tells us where something is and what its value was. Okay, and we're going to draw a hash pointer in diagrams like this. That we're going to have h of, and then an arrow that points to something. So anything drawn like this, think of it as being a hash pointer to this thing. It's a pointer to where it's stored, and it's also the hash of the value that this data had when we last saw it. And we can take hash pointers and we can use them to build all kinds of data structures. So a key idea here, take any data structure, a linked list, a binary search tree, or something like that, and implement it with hash pointers instead of pointers as we normally would. For example, here's a linked list that we've built with hash pointers. And this is a data structure that we're going to call a blockchain. So just like a regular linked list where you have a series of blocks and each block has data as well as a pointer to the previous block in the list, here the previous block pointer will be replaced with a hash pointer. So it says where it is and what the value of this entire previous block was. And we're going to remember the head of the list like this, just as a regular hash pointer. Okay. And a use case for this, for a blockchain like this, is a tamper-evident log. That is, if we want to build a log data structure that stores a bunch of data so that we can add data onto the end of the log, but if somebody goes later and messes with data that is earlier in the log, we're going to detect it. That's what the tamper evidence means. So to understand why a blockchain gives us this tamper-evident property, let's ask what happens if an adversary wants to go back and tamper with data later that's in the middle of the chain. Okay, so let's assume that an adversary wants to tamper with this block down here. He wants to change the data here, and he wants to do it in such a way that we, the holders of the hash pointer at the head here, won't be able to detect it. All right, so the adversary changed the contents of this block, and therefore the hash here, which is a hash of this entire block, is not going to match up. Because the hash function is collision-free, it must be the case that the hash of this block is now different. And so we could detect the inconsistency between this data and the hash pointer that we remembered before. Or we could do that unless the adversary also tampers with the hash pointer. If he tampers with this hash pointer, then he makes these two match up. But now he's changed the content of this block. And what that means is that when we come back later and hash the contents of this block, it's not going to match the hash that we remembered before because the contents of the block has changed. And so we're going to detect the inconsistency between the contents of this block and this hash, unless the adversary also tampers with the block over here on the right. But now when he does that, the hash of this block is not going to match the hash that we remembered up here and the hash that we're holding on to. And this the adversary can't tamper with because this is the value that we remembered as being the head of the list. And so the upshot of this is that if the adversary wants to tamper with data anywhere in this entire chain, in order to keep the story consistent, he's going to have to tamper with hash pointers all the way back to the beginning, and he's ultimately going to run into a roadblock because he won't be able to tamper with the head of the list. And so what this means is that just by remembering this hash pointer, we've essentially remembered a kind of hash, a tamper-evident hash of the entire list all the way back to the beginning. And so we can build a blockchain like this containing as many blocks as we want, going back to some special block at the beginning of the list, which we might call the genesis block. And that's a tamper-evident log built out of a blockchain. Now another useful data structure that we can build using hash pointers is a binary tree. We can build a binary tree with hash pointers, and this is called, in the jargon, a Merkle tree, after Ralph Merkle, who invented it. And the idea is this. Suppose we have a bunch of data blocks, which we'll draw across the bottom down here. We're going to take consecutive pairs of these data blocks, and for these two data blocks, we're going to build a data structure here that has two hash pointers, one to each of these blocks. And similarly all the way across. We'll then go another level up, and this block here will contain a hash pointer of these two children down here, and so on all the way back up to the root of the tree. And then just like before, we're going to remember just the hash pointer up here at the head of the tree. And we can then, if we want, traverse down through the hash pointers to any point in the list, and we can make sure that the data hasn't been tampered with. Because just like I showed you with the blockchain, if an adversary tampers with some block down here at the bottom with the data, that will cause the hash pointer that's one level up to not match, so he'll have to tamper with that, and therefore he'll have to tamper with the hash pointer one level up from there, and therefore he'll have to tamper with the hash pointer one level up from there, and eventually he'll get up to the top where he won't be able to tamper with the hash pointer that we've remembered. So again, any attempt to tamper with any piece of data across the bottom will be insured against by just remembering the hash pointer at the top. Now another nice feature about Merkle trees is that unlike the blockchain that we built before, that if someone wants to prove to us that a particular data block is a member of this Merkle tree, all they need to show us is this amount of data. So if we remember just the root, and someone wants to convince us that this block is in the Merkle tree, they need to show us this block, and we can verify that the hash matches up. And then they need to show us this block, and we can verify that the hash of this matches that. They can show us this block, we verify that the hash of this block matches this hash pointer, and then they show us the data. And just by verifying the hashes up to the root, we can verify that this data block was in the Merkle tree. So that takes about log n items that we need to be shown, and it takes about log n time for us to verify it. And so with a very large number of data blocks in the Merkle tree, we can still prove membership in a relatively short time. Okay, so Merkle trees have various advantages. One advantage, of course, is the tree holds many items, but we just need to remember the one root hash, which is only 256 bits. We can verify membership in a Merkle tree in logarithmic time and logarithmic space. That's nice. And there's a variant, which is a sorted Merkle tree. That's just a Merkle tree where we take the blocks at the bottom and we sort them into some order, say alphabetical, lexicographic order, or numerical order, or some order that we agree on. Now, having done that, once we've sorted the Merkle tree, now it's possible to verify non-membership in a Merkle tree. That is, we can prove that a particular block is not in the Merkle tree. And the way we do that is simply by showing a path to the item that's just before where that item would be and just after where it would be. And then we can say, look, both of these items are in the Merkle tree, they're consecutive, and therefore there's no space in between them. There's nothing in between them, and so the thing that we're trying to prove non-membership of can't be there. All right, so a Merkle tree is a binary search tree built with hash pointers. We can do logarithmic time membership proofs, non-membership proofs if we sort the tree, and it's very efficient. More generally, it turns out that we can use hash pointers in any pointer-based data structure, as long as the data structure doesn't have cycles. If there are cycles in the data structure, then we won't be able to make all the hashes match up. If you think about it, in an acyclic data structure, we can sort of start near the leaves or near the things that don't have any pointers coming out of them, compute the hashes of those, and then work our way back sort of toward the beginning. But in a structure with cycles, there's no end that we can start with and compute back from. So, for example, a directed acyclic graph out of hash pointers, and we'll be able to verify membership in that DAG very efficiently, and it will be easy to compute. So this is a general trick that you'll see over and over throughout the distributed data structures and throughout the algorithms that we talk about later in this lecture and in subsequent lectures. In segment 1.3, we're going to talk about digital signatures. This is the second cryptographic primitive along with hash functions that we need as building blocks for the cryptocurrency discussion later on. So a digital signature is supposed to be just like a signature on paper, only in digital form. And what that means is this. What we want from signatures is two things. First, that just like an idealized paper signature, only you can make your signature, but anyone who sees your signature can verify that it's valid. And then the second thing you want is that the signature is tied to a particular document so that somebody can't take your signature and snip it off one document and glue it onto the bottom of another one. Because the signature is not just a signature, it signifies your agreement or endorsement of a particular document. Okay, so the question is, how can we build this in a digital form using cryptography? So let's get into the nuts and bolts. Here's an API for digital signatures. There are three operations that we need to be able to do. The first one is we need, in the beginning, to be able to generate keys. And so we have a generate keys operation, and we tell it a key size. How big in bits should the keys be? And this produces two keys, SK and PK. SK will be a secret signing key. This is information you keep secret that you use for making your signature. And PK is a public verification key that you're going to give to everybody and that anybody can use to verify your signature when they see it. Okay. The second operation is the sign operation. So the sign operation, you take your secret signing key and you take some message that you want to put your signature on, and it returns SIG, which is a signature. It's just some string of bits that represents your signature. And then the third operation is a verify that takes something that claims to be a valid signature and verifies that it's correct. It takes the public key of the signer, it takes the message that the signature is supposedly on, and it takes the supposed signature. And it just says yes or no, is this a valid signature? Okay, so these three operations, these three algorithms constitute a signature scheme. And I'll note that the first two can be randomized algorithms. The verification won't be, it will always be deterministic. And in fact, if you think about it, generate keys had better be randomized because it ought to be generating different keys for different people. Okay, so the requirements for the signatures at a slightly more technical level are the following two requirements. First of all, that if a signature is, that valid signatures will verify. If a signature is valid, that is, if I sign a message with SK, with my secret key, that if someone then later tries to validate that using my public key and the same message, that will validate correctly. So this says that that signatures are useful at all. But then the second thing you want is that it's impossible to forge signatures. That is, an adversary who knows your public key, who knows your verification key, and gets to see signatures on some other messages, can't forge your signature on some message that he wants to forge it on. And in order to explain this property in a little bit more detail, it's normally formulated in terms of a sort of game that we play with an adversary. So the game, I'll depict it here with this diagram. So over here on the left, you have the challenger, who's a TV judge, and the challenger is going to test a claim by an attacker. The attacker claims that he can forge signatures, and we're going to test that claim, and the judge will pass judgment on it. The attacker here, this guy is actually Whit Diffie, who is one of the inventors of digital signatures, of the concept of digital signatures, and a distinguished cryptographer, so I thought I'd let him play the attacker role here. Okay, so the game works like this. The first thing we do is we use generate keys to generate a secret key, a secret signing key, and a public verification key that match up. Now we give the secret key to the challenger, to the judge, and we give the public key to both parties, both to the challenger and to the attacker. So the attacker only knows information that's public. He only knows the public key. And his mission is going to be to try to forge a message. The challenger knows the secret key, so he can make signatures. Right? Now, if you think about a real-life application, and a real-life attacker would be able to see valid signatures from their would-be victim on a number of different documents. And maybe the attacker could even manipulate the victim into signing innocuous-looking documents, if that's useful to the attacker. So in our game, we're going to allow the attacker to get signatures on some documents of his choice. And we see that in the diagram like this. The attacker is going to send over a message M0 to the challenger, and the challenger is going to sign that message and send the signature back. The attacker can look at that, scratch his head a little bit, and send over another message, M1. The challenger will sign that. And we do that for as long as the attacker wants. The attacker can send over any sequence of messages he wants and get signatures on them. Once the attacker is satisfied that he's seen enough signatures, and we're going to let him see only a plausible number, then he's going to pick some message M that he wants to forge a signature on, and he's going to try to forge a signature. And of course, there's a rule that says that this M, this message that he's trying to forge a signature on, isn't one of the messages that he's already seen. Because it would be really easy for him to send over a valid signature on M0. I mean, we sent him a valid signature on M0 earlier. So he's going to pick some other message that he hasn't seen a signature for already, and he's going to send over what he claims is a signature on that message. And then the question is, can he succeed? So the challenger is going to run the verify algorithm, use the public verification key, and on that message, and the signature that the attacker provided, and is going to check whether it verifies. And if it does verify, if this returns true, then the attacker wins. The attacker has forged a message. And so this game is what we use to define what it means for a digital signature scheme to have the unforgeability property. And if we want to get really precise, what we say is that the attacker's probability of winning this game is negligible, and that that's true no matter what algorithm the attacker is using. In other words, we're going to say that the signature scheme is unforgeable if, no matter what algorithm the attacker is using, the attacker has only a negligible chance of successfully forging a message. And if we have that property together with the much easier property that valid messages verify, then we have a digital signature scheme that is suitable. Okay. Now, there's a bunch of practical things that we need to do to turn that algorithmic idea into a more practically implementable signature mechanism. For example, the algorithms we talk about are randomized, at least some of them will be, and so we need a good source of randomness. And the importance of this really can't be underestimated. Band randomness will sink you, your algorithm will be insecure. And I'll just point out here that attacks on the source of randomness are a favorite trick of intelligence agencies, and those are the people who know what kinds of attacks are likely to be successful. In practice, there's a limit on the message size that you're able to sign because real schemes are going to operate on bit strings of limited length. The fix to that is simply to use the hash of the message rather than the message itself. That way the message can be really big, but the hash will be only 256 bits. And because hash functions are collision-free, it's safe to use the hash of the message as the input to the digital signature scheme rather than the message. And by the way, a fun trick, which we'll see used later, is that you can sign a hash pointer. And if you sign a hash pointer, then the signature covers or protects the whole structure. Not just the hash pointer itself, but everything it points to and everything it points to. For example, if you were to sign the hash pointer that was at the end of a blockchain, the result is that you would effectively be digitally signing the entire contents of that blockchain. That's a useful trick that we'll see used later. Okay, now let's get into the nuts and bolts. Bitcoin uses a particular digital signature scheme that's called ECDSA. That's the elliptic curve digital signature algorithm, and it's a US government standard. And we won't go into all the details of how ECDSA works. It relies on some extremely hairy math. And trust me, you don't want to see all the details of how that works. You can look it up if you're interested. So we'll skip that. One thing I'll note, though, is with ECDSA, good randomness. I said this before, but I'll say it again because it's really essential. Good randomness is especially essential with ECDSA. If you use bad randomness in generating keys or even in signing, you probably leaked your private key. It stands to reason that if you use bad randomness in generating a key, that the key that you generate is maybe not secure. But it's a quirk of ECDSA that even if you use bad randomness just in making a signature using your perfectly good key, that also will leak your private key, and then it's game over. So we need to be especially careful about this in practice. This is a common mistake. So that completes the discussion of digital signatures as a cryptographic primitive. And then in the next segment, we'll move on and talk about some applications of digital signatures that will turn out to be useful in building cryptocurrencies. In segment 1.4, we'll move on, having covered digital signatures, and talk about a nice trick that we can use that goes along with digital signatures. And the useful trick is this. The idea is to take a public key, one of those public verification keys from a digital signature scheme, and equate that to an identity. That is an identity of a person or an actor in a system. So if you see a signature that verifies correctly, that is, if you see a signature such that you can verify with someone's public key that that is a signature on a particular message, then you can think of that as that public key saying the message. You can literally think of a public key as kind of like an actor or a party in a system, and that they can make statements by signing those statements. And so if you think in that mindset, then this public key is like an identity. It's an actor who can do stuff in the system. And if you think about it then, for someone to speak for PK, that is for someone to be able to make statements that will be seen as coming out of PK's mouth, you have to know the matching secret key, SK. And so if you know the secret key that corresponds to the public key, PK, then you can sign messages with that secret key, and what you're doing essentially is making statements on behalf of that public key. And that means that there is an identity in the system which only you can speak for. And of course, that's what you want an identity to be, something that one person can speak for or on behalf of that everybody can see. All right, so if we're going to treat public keys as identities, one of the consequences of that is that you can make a new identity whenever you want. If you want to make a new identity, you just do this. You create a new random key pair, SK and PK, by doing the generate keys operation in our digital signature scheme. And we get out SK and PK. PK is then the public name that you can use. That's the name of that identity, what it's called. Although in practice, you'd probably use the hash of PK because public keys are big. But again, we'll leave that aside as a detail. So PK, or the hash of it, is the public name that you use to talk about the identity. And SK, the secret key, is the information that lets you, the person who generated this identity, speak for the identity. You control the identity because only you know the secret key. And if you generated this in such a way that the public key PK looks random, then nobody needs to know who you are. You can generate a fresh identity that looks random, that looks like a face in the crowd, that only you can control. This brings us to the idea of decentralized identity management. That rather than having a central place that you have to go in order to register as a user in a system, you don't need to get a username, you don't need to inform someone that you're going to be using a particular name. If you want a new identity, just make one. Anybody can make a new identity at any time, and you can make as many as you want. If you prefer to be known by 5 different names, no problem, just make 5 identities. If you want to be somewhat anonymous for a while, you can make a new identity, use it just for a little while, then throw it away. All of these things are possible with decentralized identity management, and there's no central point of control, so that you don't have to have anyone who's in charge of it. The system operates in an entirely decentralized way. And this is the way Bitcoin, in fact, does identity. These identities are called addresses in Bitcoin jargon. And so you'll hear the term address used in talking about Bitcoin and cryptocurrencies. But what that really is just a public key or a hash of a public key. It's an identity that someone made up out of thin air as part of this decentralized identity management scheme. Now, the obvious question that arises when you're talking about decentralized identity management and people making up these identities is, how private is this? And the answer is, it's complicated. On the one hand, the addresses that are made up this way are not connected to your real-world identity. You can execute a randomized algorithm. It will make some kind of PK that looks kind of random, and nothing exists initially to connect that to who you are. You can do that in the privacy of your own home. So that's good news if you want to be able to act privately. But the bad news if you want to act privately is that if that address, if that identity is making a series of statements over time, if it's engaging in a series of acts over time, that people can see that whoever this is has done a certain series of actions. And they can start to connect the dots. Gee, this person is acting a lot like Joe. Maybe this person is Joe. And so an observer can link together these things over time and make inferences. And so this balance between, on the one hand, there being no initial tie to real-world identity, and on the other hand, that a pattern of behavior of an address emerging over time, and the question of what can be inferred and which dots can be connected, that gets pretty complicated. And that's really the question of privacy in a cryptocurrency like Bitcoin. And there's a whole lecture about that later on. And so I'm not going to steal the thunder of that lecture. I just want to give you an idea of how decentralized identity makes privacy a complicated question.
With a simple currency that we called Scrooge coin that seems to achieve a lot of what we want in a ledger-based cryptocurrency, except for one big glaring problem, which is that it relies upon the centralized authority called Scrooge. And we ended with the question of, how do we de-Scroogify this currency? How do we go to a decentralized version of this? That's what we're going to see today. What I find cool about this is that the way in which Bitcoin achieves decentralization is not purely technical, but it's a combination of technical and clever incentive engineering. And at the end of this lecture, you should have a really good appreciation for how this happens, and a lot of the magic or the mystery of Bitcoin should become clear to you, and how it works, and why it's secure, and what makes it tick. So it turns out that decentralization is an important concept not just for Bitcoin, but in fact, this notion of competing paradigms of centralization versus decentralization plays out in a variety of different digital technologies. To understand Bitcoin's decentralization, I want to start with the caveat that decentralization almost always is not all or nothing. Almost no system is purely decentralized or purely centralized. And a good example of this is email, which is a decentralized system fundamentally, I would say. It's based on a standards-based protocol, SMTP, but What has happened, especially in the last decade or so, is that we see a dominance of a few different webmail providers, which are sort of centralized service providers, and this might be a good model for understanding what might be happening to Bitcoin. So with that, let's delve into some of the technical aspects of Bitcoin's decentralization, and I would break this down into at least 5 different questions. Questions like, who maintains this ledger of transactions? Who has authority over which transactions are valid? Who creates new Bitcoins? And in fact, other questions like, who determines how the rules of the system change and how do Bitcoins acquire exchange value? So these are all components of decentralization of the Bitcoin protocol, more or less. And the first 3 of these are going to be the questions that we will consider in this lecture. And when I say, how is Bitcoin decentralized, what I mean encompasses the first 3 of these meanings. And I want to emphasize that there are aspects to decentralization beyond the protocol. That includes things like Bitcoin exchanges, where you can convert Bitcoin into other currencies. It includes things like wallet software and a variety of other service providers. And so even though the underlying protocol is decentralized, these services that develop on top of it may be centralized or decentralized to varying degrees. And just to drive home this point, let me show you 3 different aspects of Bitcoin and where they fall on the centralization-decentralization spectrum. First, there's the peer-to-peer network. And this aspect of Bitcoin, I would say, is the closest thing to purely decentralized. Why is that? Because anybody can run a Bitcoin node, and there's a fairly low barrier to entry. You can go online, you can download a Bitcoin client yourself. It requires a lot of disk consumption on your computer, but basically you can run that on your laptop or your PC yourself. And currently there are several thousand Bitcoin nodes, and so this really resembles a peer-to-peer decentralized system. But that's not the only component of Bitcoin. There's also Bitcoin mining, which we'll study later in this lecture. And Bitcoin mining is technically also open to anyone, but it turns out that it requires a very high capital cost. It's a consequence of how the system happens to have evolved. And because of this, there has been a high centralization or a concentration of power in the Bitcoin mining ecosystem. And the community frequently sees this as quite undesirable. So this aspect of Bitcoin is not quite as decentralized as one might want it to be. And here's a third aspect, updates to the software. And this really gets to how and when the rules of the system change. And once again here, one can conceptually imagine that everybody running a Bitcoin node will look at the Bitcoin specification and maybe even create their own software. And again, you have a purely decentralized system. But of course, that's not how it works in practice. The core developers are really trusted by the community, and they have a lot of power when it comes to determining what Bitcoin software each of these nodes will run on their computer. So we've talked in a generic manner about centralization and decentralization. Let's now talk at a bit more technical level about Bitcoin and decentralization. And a key word that's going to come up again and again here is consensus, specifically distributed consensus. So what am I talking about here? At a technical level, the key challenge that you have to solve to build a distributed eCash system is called distributed consensus. And this is a class of protocols that's been studied for decades in the computer science literature. But intuitively, you can think of it as our goal being to decentralize Scrooge coin, which is the hypothetical currency that we saw in the first lecture. So as I said, there's decades of research in computer science on these consensus protocols, and the traditional motivating application for this is reliability in distributed systems. What do I mean by that? Imagine you're in charge of the backend for a company like Google or Facebook. These companies typically have thousands or even millions of servers, which form a massive distributed database that records all of the actions that happen on the system, like users' comments and likes and posts and so on. So when a new comment, let's say, comes in, the way it'll be recorded is that there might be 10 or 15 different nodes in that massive backend that might contain copies of this action. Now, what the server needs to make sure is that that comment either gets recorded in all copies of that database or none of them. If for some reason, because some of these nodes might be faulty, the action gets recorded in none of the databases, it's okay. You can go back to the user and say, there was a problem saving your post, would you please try again? On the other hand, if some of the copies of the database saved it and others didn't, then you'd be in a lot of trouble because you'd have an inconsistent database. So this is the key problem that motivated the traditional research on distributed consensus, and you can sort of see the similarities to Bitcoin here, but we're going to talk in a bit more detail about the similarities and differences. So that was the traditional motivating application, but we can also imagine that if we achieved a distributed consensus protocol, and we were able to use that to build a massive global scale distributed key value store that maps arbitrary keys or names to arbitrary values, then that will enable a lot of applications. For example, a distributed domain name system, which is simply a mapping between human understandable domain names to IP addresses. Or a public key directory, which is a mapping between user email addresses, let's say, to their public keys. Or even things like stock trades, because this distributed database, instead of keeping track of who's paid whom how much money, would keep track of who's transferred what units of which stock to whom. And the cool thing about this is that now that Bitcoin has solved the distributed consensus problem in a certain sense that we'll try to understand in this lecture, we can also go ahead and try to think about solutions to all of these other related problems. And in fact, there are many altcoins. And altcoins, we'll have several more lectures about altcoins, but very briefly, altcoins are systems built on Bitcoin-like principles to achieve perhaps slightly different goals. Sometimes currency systems, sometimes not currency systems, such as one of these applications. And so, given that we can solve distributed consensus now, and given that we can build a global distributed key value store, it enables a lot of these other cool applications. Okay, let's go to a technical definition now. The technical definition of distributed consensus is really quite simple. Imagine that there is a fixed number n of nodes or processes, and each of these nodes has some input value. And then a consensus protocol happens, and the two requirements on this consensus protocol are that the protocol should terminate, and all correct nodes should decide on some value, the consensus value. Right? And I say correct nodes because some of the nodes might be faulty or even outright malicious. And the second requirement is that this value that they agree upon cannot be an arbitrary value, but it should be a value that was proposed as input by at least one of these correct nodes. So it's really that simple, but let's try to see what this might mean in the context of Bitcoin. So to understand how distributed consensus could work in Bitcoin, let's start with a reminder that Bitcoin is a peer-to-peer system, right? So what I mean when I say that Bitcoin is a peer-to-peer system is that when Alice wants to pay Bob, what she does is she's going to broadcast a transaction to all of the Bitcoin nodes that comprise the peer-to-peer network. And you can see here the structure of the transaction. This is similar to Goofy Coin that we saw in the first lecture. And what a transaction is going to have is it's going to have Alice's signature, which the other nodes need in order to know that it really in fact came from Alice. It's going to have Bob's public key, which also acts as his address at which he wants to receive Bitcoins. And further, it contains a hash. What is this hash? Recall this notion of hash pointers that we saw in the first lecture. So this hash is a way for Alice to link together this transaction or this coin to her receipt of this coin from someone else previously. Right? So those are the things that are contained in this data structure that we call a transaction, and she's going to broadcast that to all of the Bitcoin peer-to-peer nodes. And notice something funny here. Bob's computer is nowhere in this picture. Now Bob, if he wants to be notified that this transaction did in fact happen and that he got paid, he might want to run a Bitcoin node that's one of these peer-to-peer nodes in order to listen in on the network and be sure that he's received that transaction, but his listening is not in fact necessary for him to receive the funds. The Bitcoins will be his whether or not he's running a node on the network. So given this peer-to-peer system, what is it exactly that the nodes might want to reach consensus on? Well, given that a variety of users are broadcasting these transactions to the network, what everybody wants to reach consensus on is exactly which transactions were broadcasted and the order in which these transactions happened. Right? So what does that mean specifically? How consensus could work in Bitcoin is that at any given time, all the nodes in the peer-to-peer network would have a sequence of blocks of transactions that they've reached consensus on. So recall that in Scrooge Coin, for optimization purposes, for efficiency, we put transactions into blocks and we link these blocks together on a blockchain. So we're utilizing a similar principle here. We could do consensus on transactions one by one. That would be okay. It would just be inefficient. So instead, we do consensus on a block by block basis. So at any given point, all these nodes in the peer-to-peer network would have the sequence of blocks that they've agreed upon already. And each node would then have a set of outstanding transactions that it has heard about. So recall that for these transactions, consensus has not yet happened. And so almost by definition, each node might have a slightly different version of the outstanding transactions that it's heard about. The peer-to-peer network is not perfect, so some node may have heard about a transaction, but not other nodes. So given that we have the setup, what could happen is that you have the sequence of blocks that everybody has agreed upon. A block is just a series of transactions. And now there are these, let's say, these three nodes in the system, each of whom proposes, each of whom has an input, the set of outstanding transactions that it's heard about. And they execute together some consensus protocol. And for the consensus protocol to succeed, you can select any valid block, even if it's a block that was proposed by only one node. And for a block to be valid, all of these transactions have to have the right crypto signatures and so on. So you could select any of these valid blocks and the consensus protocol would still be okay. If some transaction somehow didn't make it into this particular block that gets chosen as the result of a consensus protocol, it could just wait and get into the next block. Right? So maybe this green block gets selected, it gets added to the consensus blockchain, and then the protocol proceeds in rounds. So if you took the traditional theory of distributed consensus and applied that to Bitcoin, this is the sort of system that you might end up with. Now this has some similarities to how Bitcoin works, but it's not exactly how Bitcoin works. And why is that? And the reason for this is simple. Doing things this way is a really hard technical problem for a variety of reasons. There are some obvious ones. Nodes might crash and nodes might outright be malicious. But also because the network is highly imperfect. It's a peer-to-peer system. Not all pairs of nodes are connected to each other. There could be faults in the network because of poor internet connectivity and so on. And finally, there's going to be a lot of latency in the system because all of these things happen over the internet. They're not even within a single data center or something like that. And one particular consequence of this high latency is that there is no notion of global time. What does this mean and why is this important? It means that not all nodes can agree to a common ordering of events simply based on observing timestamps. It just doesn't work like that. So you can't possibly design your protocol by saying things like, take the node that sent the first message in step 1 and have that node do something in step 2. You just can't work like that because not all nodes will agree on which message was sent first in the first step of the protocol. So this really puts serious constraints on what sorts of algorithms you can really put into your consensus protocols. And in fact, because of these constraints, a lot of the literature on distributed consensus is somewhat pessimistic, and many impossibility results have been proved. I'm just going to name a couple of these in case you want to look them up, but I won't go into too much detail. One impossibility result that's very well known and pretty simple to understand is called the Byzantine generals problem. And a much more subtle one, known for the names of the authors who first proved it, is called the Fisher-Lynch-Patterson impossibility result. Under some conditions, which include the nodes acting in a deterministic manner, what they proved is that consensus is impossible even with a single faulty process. So despite these impossibility results, there are a few well-known protocols, and Paxos is probably one of the better known. And what Paxos does is it makes certain compromises. What it gives you is that it never produces an inconsistent result, which would be really bad, but it accepts the trade-off that under certain conditions, albeit rare ones, the protocol can get stuck and fail to make any progress. But here's the interesting thing. These impossibility results were, they were proved in a different model. They were intended to study distributed databases. And this model doesn't carry over that well to this setting that Bitcoin operates under. So what these results really tell us more about the model than about the problem, in fact. And what Bitcoin does is that it violates a lot of the assumptions that go into these models, and because of that, consensus in Bitcoin ironically works better in practice than in theory. And what this really means is that the theory that was developed for a different set of problems needs to catch up in order to be able to say really interesting things about Bitcoin. But nevertheless, that theory is quite important because, for example, it can help us predict unforeseen attacks and really be able to come to strong guarantees on the nature of consensus and security in Bitcoin. So what are these different assumptions? What are some things that Bitcoin does differently? Well, first of all, it introduces the idea of incentives. And this is very different from any previous system for distributed consensus. And this is only possible in Bitcoin because it is a currency, and you can use that currency to give incentives to the participants for acting honestly. And so Bitcoin doesn't quite solve the distributed consensus problem in a general sense, but it solves it in the context of a currency system. And the other thing that it does differently is that it really embraces the notion of randomness. And what I mean by that is one of the things it does is it does away with the notion of a specific starting point and ending point for consensus. Instead, consensus happens over a long period of time, about an hour in the practical system, but even at the end of that time, you're not 100% sure that a transaction or a block that you're interested in has made it into the consensus blockchain. Instead, as time goes on, your probability goes up higher and higher, and the probability that you're wrong in making an assumption about a transaction goes down exponentially. So that's the kind of inherently probabilistic guarantee that Bitcoin gives you, and that's why it's able to completely get around these traditional impossibility results on distributed consensus protocols. So let's now dig into the technical details of Bitcoin's consensus algorithm. And while we're looking at that, we should keep in mind that Bitcoin does all of this without nodes having any persistent long-term identities. And this is yet again a difference from how traditional distributed consensus algorithms operated. And if nodes did have identities, it would make things a lot easier for a couple of reasons. One is a pragmatic reason. It would allow you to put into your protocol things like, now the node with the lowest numerical ID should take some step or something like that. So that's a simple pragmatic reason, which already, if nodes are completely anonymous, becomes harder to do. But a much more serious reason for nodes to have identities is for security, because if nodes were identified and it weren't trivial to create new node identities, then we could make assumptions like, let's say that less than 50% of the nodes are malicious, and we could derive security properties out of that. So for both of these reasons, the consensus protocol in Bitcoin is a bit harder. But why is it exactly that Bitcoin nodes don't have identities? Well, it's for a couple of reasons. One is that if you're in a decentralized model, in a peer-to-peer system, there is no central authority to give identities to nodes and verify that they're not creating new nodes at will. And in fact, the technical term for this is a Sybil attack. Sybils are just copies of nodes that a malicious adversary can create to look like there are a lot of different participants, when in fact all those pseudo-participants are really controlled by the same adversary. The other reason is that pseudonymity is inherently a goal of Bitcoin. Even if it were possible or easy to establish identities for all nodes or all participants, we wouldn't necessarily want to do that. So Bitcoin doesn't give you strong anonymity guarantees out of the box, in that the different transactions that you make can probably be linked together, but at the same time, nobody is forcing you to put your real-life identity, like your name or IP address or anything like that, in order to participate in the peer-to-peer network and in the blockchain, and that's an important property. So what we can do instead is we can make a weaker assumption. And I kind of want you to take a leap of faith with me here, that this weaker assumption is something that is going to be feasible. And I'm going to make this assumption here and later show you how this is actually accomplished. And what this weaker assumption is that we're going to assume that there is some ability somehow to pick a random node in the system. And a good motivating analogy for this is a lottery or a raffle or any number of real-life systems where tracking and verifying people and giving them identities and verifying those identities is pretty hard. And so what we do in those contexts is we might give them tokens or tickets or something of that sort, and that then enables us to later pick a random token ID and call upon that person. So we're going to do something similar with respect to these Bitcoin nodes and further assume for the moment that this token generation and distribution algorithm has enough smarts so that if the adversary is going to try to create a lot of Sybil nodes, together all of those Sybils just get one token, so the adversary is not able to multiply his power that way. So let's make this assumption for now, and let's see what becomes possible if we make this assumption. Here's the key idea. What becomes possible under this assumption of random node selection is something called implicit consensus. So what is implicit consensus? In each round, and there are going to be multiple rounds, each round corresponding to a different block in the blockchain. In each round, a random node is somehow selected, magically for the moment. And this node gets to propose the next block in the chain. There is no consensus algorithm, there is no voting. This node simply unilaterally proposes what the next block in the blockchain is going to be. But what if that node is malicious? Well, there is a process for this, but it is an implicit one. Other nodes will implicitly accept or reject that block. And how will they do that? If they accept that block, they will signal that acceptance by extending the blockchain starting from that block, or if they reject that block, they will extend the chain by ignoring that block and starting from whatever was the previous latest block in the blockchain. And technically, how is that implemented? Recall that each block contains a hash of the block that it extends, and this is the technical mechanism that allows nodes to signal which block it is that they're extending. So given this is what the overall consensus algorithm in Bitcoin is going to look like. Now, this is a little bit simplified, and the reason it's simplified is, again, that I'm assuming sort of this magic random node selection process. But except for that simplification, this is pretty close to how Bitcoin actually works. So whenever Alice wants to pay Bob, she will create a transaction, and she will broadcast it to all of the nodes. And any one of these nodes is constantly listening to the network and collecting a list of outstanding transactions that have not yet made it into the blockchain. At some point, one of these nodes is going to be randomly called upon to propose the next block. It's going to round up all of the outstanding transactions that it's heard about and propose that block. Now, presumably that node was honest, but it could also be a malicious node or a faulty node and propose a block that contains some invalid transactions. Invalid transactions are those that don't have the right crypto signature or where the transaction is already spent. In other words, an attempt to double spend. So if that happens, other nodes are going to signal their acceptance or rejection of the block, as we saw on the last slide, by either including the hash of this latest block in their next block, or ignoring this block and including the hash of whatever was the previous block that they considered to be valid. Right. So now let's try to understand why this consensus algorithm works. And the way I like to understand this is, instead of asking why this works, let's try to ask, how can a malicious adversary try to subvert this process? So let's look at that for a second. So here we have a couple of blocks in the blockchain. Assume that this extends to the left a long way back, all the way to what is called the genesis block. But here I'm only showing you a couple of blocks in the blockchain. And that pointer that you see over there is a block referring to what is the previous block that it extends by including a hash of that previous block within its own contents. So a malicious attacker, let's call her Alice. What might she try to do? Can she simply steal Bitcoins belonging to another user at a different address that she doesn't control? Now, even if it is now Alice's turn to propose the next block in this chain, she cannot steal other users' Bitcoins. Why? Because she cannot forge their signatures. So as long as the underlying crypto is solid, she's not able to simply steal Bitcoins. Another thing she might try to do is, if she really, really hates some other user, Bob, then she can look at Bob's address and she can decide that any transactions originating from Bob's address, she will simply not include them in any block that she proposes to get onto the blockchain. In other words, she's denying service to Bob. So this is a valid attack that she can try to mount. But luckily, it's nothing more than a little annoyance, because if Bob's block doesn't make it into the next block that Alice proposes, he will just wait another block until an honest node gets the chance to propose a block, and then his transaction will get into that block. So that's not really a good attack either. So the only one that we're really left with for what a malicious node can try to do here is called a double spending attack. So how might a double spending attack work? To understand that, let's assume that Alice is a customer of some online merchant or a website run by Bob, who provides some online service in exchange for payment in Bitcoins. Let's say he allows the download of some software. So here's how a double spending attack might work. Alice goes to Bob's website and decides to buy this item, pays for it with Bitcoins, and what that means in technical terms is that she's going to create a Bitcoin transaction from her address to Bob's address. She broadcasts it to the network, and let's say that some honest node creates the next block, listens to this transaction, and includes it in that block. So what is going on here? So there is this block that was created by an honest node that contains a transaction that represents a payment from Alice to the merchant Bob. By C subscript A, I mean a coin belonging to Alice, and that is now being sent to Bob's address. Let's zoom into this in a little bit more technical detail. A transaction, as we saw earlier, is a data structure that contains Alice's signature here and an instruction to pay to Bob's public key, and also a hash. What is this hash? This hash represents a pointer to the transaction where Alice in fact received that coin from somebody else, and that must be a pointer to a transaction that was included in some previous block in the consensus chain, so visually it's going to look something like this. Let's pause for a second here because there's something subtle going on. There are at least two different types of pointers in this diagram that I've showed you. There's in fact a third one corresponding to Merkle trees, but we're not going to look at that at the present moment. But these two types of pointers that I refer to are blocks that include a hash of the previous block that they're extending, and transactions that include a pointer to whatever the previous transaction where the coin came from. Right, so this is the situation, and this block was now generated by an honest node. And now let's assume that the next time a random node is called, that node is a malicious node controlled by Alice. Right, so this is the blockchain as it stands right now. Bob has already looked at this blockchain, decided that Alice has paid him, and has allowed Alice to download the software or whatever it is that she was buying on his website. Right. So as far as Bob is concerned, he's satisfied, the transaction is completed. Alice has now received her goods in exchange for the payment. Now what might happen is if Alice now gets to propose the next block, she could propose a block that looks like this, ignores altogether this valid block over here, and instead contains a pointer to the previous block. And furthermore, it's going to contain a transaction that contains a transfer of coins, of Alice's coins, to another address, A prime, that's also controlled by Alice. So this is a classic double spend pattern. What is going on here is Alice now creates a new transaction that transfers that coin instead of to Bob's address to another address owned by her. And visually it's going to look like this. This is a completely different transaction, also with a hash pointer going back to the same transaction referred to earlier. Right? So this is what an attempt at a double spend look like. And how do we know if this double spend attempt is going to succeed or not? Well, that depends on whether this green transaction here or this red transaction is going to ultimately end up in the long-term consensus chain. So what determines that? That is determined by the fact that honest nodes are always following the policy of extending the longest valid branch. So now, which of these is the longest valid branch? You might look at this and say, aha, the first one is the longest valid branch, not the second one, because it's a double spend attempt. But here's a very subtle point that I want you to appreciate. From sort of a moral point of view, this transaction in green and the transaction in red might look very different because based on the explanation that I've given you, the first one is an attempt by Alice to pay Bob, whereas the second one is an attempt by Alice to defraud Bob and pay coins back to herself. But from a technological point of view, these two transactions are completely identical. The nodes that are looking at this really have no way to tell which one is the legitimate transaction. I'm putting legitimate in air quotes because it's a moral judgment that we apply to it. It's not a technical distinction. Versus which one is the attempted double spend. It could easily be the other way around. Now, nodes often follow a heuristic of extending the block that they first heard about on the peer-to-peer network, but it's not a solid rule, and in any case, because of network latency, that could easily be the other way around. So now there is at least some chance that the next node that gets to propose a block will extend this block instead of this one. Or it could be that even if it's an honest node, Alice could try to bribe that node or try to subvert the process in a variety of ways. So for whatever reason, without going too much into the details, let's say that the next node extends the block with the red transaction instead of the green one. What this means is that at this point, the next honest node is much more likely to extend this block instead of this one because now this has become the longest valid chain. So let's say that after one more block, the situation looks like this. Now it's starting to look pretty likely that this double spend has succeeded. In fact, what might happen is that this ends up the long-term consensus chain, and this block gets completely ignored by the network, and this is now called an orphan block, and this is an example of a successful double spend. So now let's look at this whole situation from Bob the merchant's point of view. And understanding how Bob can protect himself from this double spending attack is really going to be a key part of understanding Bitcoin security. So let's look at what happened here again. We have a couple of blocks in the blockchain. And at this point, Alice broadcasts a transaction that represents her payment to Bob. And so Bob is going to hear about it on the peer-to-peer network right here, even before the next block gets created. And so Bob can do something even more foolhardy than what he did in the previous slide, which is that as soon as he hears about the transaction on the peer-to-peer network, he can complete the transaction on the website and allow Alice to download whatever she's downloading. That's called a zero confirmation transaction. Or he could wait until the transaction gets one confirmation in the blockchain, which means that at least some node has created a block and has proposed this transaction, and that has gone into the blockchain. But as we saw earlier, even after one confirmation, there could be an attempt at a double spend. So let's say that this actually happens. If, as in the previous slide, the double spend attempt succeeds, what Bob should do is to realize that the block that he thought represented Alice paying him has now been orphaned, and so he should abandon the transaction. Instead, if it so happens that despite this double spend attempt, the next block that's generated turns out to extend the block that he's interested in. Now he sees that his transaction has two confirmations in the blockchain. Now he gets a little bit more confidence that his transaction is going to end up on the long-term consensus chain. So let's say there's one more, and now there are three confirmations. In general, the more confirmations your transaction gets, the higher the probability that it is going to end up on the long-term consensus chain, because if you recall the honest node's behavior, that they will always extend the longest valid branch that they see, the chance that this one is going to catch up to this longer branch is now very minuscule, especially if only a minority of the nodes are malicious. Right? Because typically, the only reason that this double spend attempt block would be extended at this point is if the next node to be picked randomly was a malicious node, and then you'd need another malicious node and then another for the shorter branch to then become the longer branch. In general, the double spend probability decreases exponentially with the number of confirmations. So if the transaction you're interested in has received k confirmations, then the probability that this other transaction is going to end up on the long-term consensus chain goes down exponentially as a function of k. And the most common heuristic that's used in the Bitcoin ecosystem is that you wait for 6 confirmations. There is nothing really special about the number 6. It's just a good trade-off between the amount of time you have to wait and your guarantee that the transaction you're interested in ends up on the consensus blockchain. So let's recap what we saw here. Protection against invalid transactions, that is, protection against a malicious node simply making up a transaction to steal someone's bitcoins, is entirely cryptographic, but it is enforced by consensus, which means that if a node does attempt that, then the only reason that that transaction won't end up in the long-term consensus chain is because a majority of the nodes are honest and will treat that transaction as invalid. On the other hand, protection against double spending is purely by consensus. Cryptography has nothing to say about this, and true transactions that represent a double spending attempt kind of look identical from the perspective of signatures and so on, but it's the consensus that determines which one will end up on the long-term consensus chain. And finally, you're never 100% sure that a transaction you're interested in is on the consensus branch, but this exponential probability guarantee is pretty good. After about 6 transactions, there's virtually no chance that, that you're going to go wrong. So in the previous section, we got a basic look at Bitcoin's consensus algorithm and a good intuition for why we believe that it's secure. But recall that at the beginning of the lecture, I told you that Bitcoin's decentralization is partly a technical mechanism and partly clever incentive engineering. So far, we've mostly looked at the technical mechanism. Now let's talk about the incentive engineering that happens in Bitcoin. I asked you to take a leap of faith with me earlier in assuming that we're able to pick a random node, and perhaps more problematically, that at least 50% of the time this process will pick an honest node. But of course, this assumption of honesty is quite problematic, especially if there are financial incentives for participants to subvert this. Then why would we expect any node to be honest, really? So what we want to ask is, can we give nodes an incentive for behaving honestly? Let's look at this with respect to the picture we've been looking at. This is the long-term consensus chain, and this block contains an attempt to double spend. We can ask, can we penalize somehow the node that created this block? But this is problematic for a number of reasons, including the fact that nodes don't have identities, and so there's no way to go after them to penalize them. So instead, let's flip the question around and ask, can we reward the nodes that created all these blocks that did end up on the long-term consensus chain? Well, again, sort of the same problem. We don't have node identities, so we can't mail them cash to their home addresses. If only there were some sort of digital currency that we can use to incentivize them, a decentralized one perhaps. You probably see where I'm getting at. In other words, we're going to use bitcoins in order to incentivize the nodes that created these blocks. So how are we going to do that? Well, so far, everything that I've said is just an abstract algorithm for achieving distributed consensus. Now we're going to break out of that model. What I'm going to say now is specific to the fact that what we're achieving through this distributed consensus process is in fact a currency. And we're going to incentivize these nodes by paying them in units of this currency. So how do we do that? There are in fact two separate incentive mechanisms in Bitcoin, and the first one is called the block reward. So what is the block reward? It's just this. According to the rules of Bitcoin, the node that creates each block gets to include a special transaction in that block, and that special transaction is a coin creation transaction. And this node can also choose the recipient address of this transaction. So of course that node will typically choose an address belonging to itself as the recipient of this coin creation transaction, thereby paying itself. It's sort of, you can think of it as a payment in exchange for the service of creating that block to go onto the consensus chain. In fact, the value of this coin creation transaction has an interesting property. It's currently fixed at 25 bitcoins, but it actually halves every 4 years. We're now in the second period. For the first 4 years of Bitcoin's existence, it was 50 bitcoins. Now it's 25, and it's going to keep halving. This has some interesting consequences. We'll come back to that in the next slide. But let me ask you this. It appears, based on what I've said here, that this node gets the block reward regardless of whether it proposes a block with only valid transactions or it behaves maliciously. So how are we actually providing any incentives for honest behavior via this block reward? But think about this. Well, how will this node sort of get to collect its reward? That will only happen if this block ends up on the long-term consensus branch, because that's the only case in which this coin creation transaction will be considered valid, because the coin creation transaction is not special. It's just like every other transaction. It's only valid if it ends up on the consensus chain. So that's the incentive mechanism here. It's very subtle, but it's a very neat trick. And so it incentivizes nodes to behave honestly, or at the very minimum, it incentivizes nodes to behave in a way that they think other nodes are going to agree with in creating the next blocks of the blockchain. So that's the first incentive mechanism. Let's come back to this point now, this weird sort of halving phenomenon that we see here. And this can be best illustrated graphically. Here I'm going to show you a graph of time on the x-axis versus the total number of bitcoins in circulation. And this over here was the first period where each block resulted in 50 new bitcoins being created. And roughly at the end of last year, that block reward halved from 50 to 25. And you can see that every 4 years, extending well into the future, the slope of this curve is going to keep halving. And this is a geometric series, and you might know that it means that there is a finite sum. And in fact, there is a total finite supply of bitcoins. And if you add up all these numbers, it works out to 21 million based on the rate of new block creation, which I'm going to get to in a second. Also worth noting is that this is the only way in which new bitcoins are created. There is no other coin generation mechanism, and that's why this is a final and total number, as the rules stand now at least, for how many bitcoins there can ever be. And this new block creation reward is actually going to run out. So that sounds a bit weird. Does that mean that the system will stop working and become insecure because nodes no longer have the incentive to behave honestly? Well, not quite. because this is only the first of two incentive mechanisms. There is quite another incentive mechanism called the transaction fee. And what is a transaction fee? So the creator of any transaction, not the creator of a block, but the creator of a transaction, when Alice is paying Bob, what she can do is she can choose to make the output value of that coin less than the input value. And the way that all the nodes interpret this difference, according to the rules of Bitcoin, is that it's a transaction fee. And whoever creates the block that first puts that transaction into the blockchain gets to collect that transaction fee. So if you're a node that's creating a block that contains, say, 200 transactions, then the sum of all those 200 transaction fees accrues to you and to the address that you put into that block. Of course, this transaction fee is purely voluntary, like a tip, but we expect, based on our understanding of the system, that as the block reward starts to run out, it'll become more and more important, almost mandatory, for nodes to put a transaction fee into their transactions in order to get a reasonable quality of service. And to a certain degree, this is already starting to happen now. But precisely how the system will evolve, it really depends on a lot of game theory, which hasn't been fully worked out yet. So that's an interesting area of open research in Bitcoin. So now we've acquired an understanding of how the nodes that create these blocks are incentivized to act honestly or follow the protocol. And so if we address a few more of these remaining problems, we'll be all set to have a really good understanding of how Bitcoin achieves decentralization. What are these remaining problems? Well, one of them, the first major one, is the leap of faith that I asked you to take, which is that somehow we can pick a random node. And the second is that we've created a new problem by giving nodes these block rewards and incentives, which is that you could easily get into a free-for-all where everybody wants to run a Bitcoin node in the hope of capturing some of these rewards. And a third one is an even trickier version of this problem, which is that an adversary might create a whole different number of Sybil nodes in order to really try to subvert this consensus process. So number 3 is sort of a trickier version of number 2. It turns out that all of these problems are related, and all of them have the same solution. And that solution is called proof of work. So what is proof of work? Here's the key idea. Instead of picking a random node, we do something a little bit different, which is we approximate selecting a random node by instead selecting nodes in proportion to a resource that we hope that nobody can monopolize. What does that mean? Well, if that resource that we're talking about is computing power, then it's a proof of work system where we somehow select nodes in proportion to their computing power. Alternately, it could be in proportion to ownership of the currency, and this is a legitimate alternate model. It's not used in Bitcoin, but it's been proposed and it's used in a lot of alternatives to Bitcoin, and that's called proof of stake, which we'll see in a later lecture. But let's come back to proof of work. Let's try to get a better idea of what this means. Selecting nodes in proportion to their computing power, another way to understand this is that we're allowing nodes to compete with each other by using their computing power. And that will result in nodes automatically being picked in that proportion. So those are two equivalent ways to view proof of work. You can also think of a third way, which is that we're making it moderately hard through proof of work to create new identities. So it's sort of a tax on identity creation and on the Sybil attack. This may all appear a bit vague, so let me actually go ahead and show you what is the exact proof of work system that's used in Bitcoin, and that's going to make things a lot clearer. So here it is. It's called hash puzzles, and what this means is that in order to create a block, the node that proposes that block is required to find a number, a nonce, such that when you put together in the block the nonce, the previous hash, and the list of transactions that comprise that block, and take the hash of this whole long string, then that hash output should be a number that is very small, that falls into this small target space here in relation to this very large space that is the output space of that hash function. Let's look at it one more time. As we looked at it earlier, normally a block contains a series of transactions that you're proposing. In addition, a block also contains a pointer to the previous block, as we saw, and a pointer is just a string in this context. But in addition here, we're requiring that a block also contain a nonce. And why is this? And the idea is that we want to make it moderately difficult to, in fact, find a nonce that satisfies this required property, which is that hashing the whole block together, including that nonce, is going to result in a particular type of output. And so we believe that if the hash function is secure, then the only way to succeed in solving this hash puzzle is to just try enough nonces one by one until you get lucky. So specifically, if this target space were just 1% of the overall output space, you would have to try about 100 nonces before you got lucky. And if this hash function were to behave essentially randomly, only 1 in 100 nonces will result in an output that falls within this target space. In fact, the size of this target space is not nearly as high as 1% of the output space. It's much, much smaller than that, which we'll get to in a second. But fundamentally, this is the computational problem that a node is required to solve in order to produce the block. Now, this notion of hash puzzles and proof of work completely does away with the requirement for somebody somehow to pick a random node. Instead, nodes are simply all the time independently competing to solve these hash puzzles. And once in a while, one of them will get lucky and will find a random nonce that satisfies this property. And that node then gets to propose the next block. That's how it's completely decentralized. There is nobody deciding which node it is that gets to propose the next block. So let's look at it in a little bit more detail now. There are 3 properties that I want to show you, essential properties of this proof of work function, of this hash puzzle. And the first is that it needs to be quite difficult to compute. I said moderately difficult, but what I mean by moderately difficult, as of today, and you'll see why it varies with time, it's about 10 to the 20 hashes per block that you need to compute. So the size of the target space is only 1 over 10 to the 20 of the size of the output space of this hash function. Right, so if you look at it in terms of the amount of computing that your laptop needs to do, for example, this is simply a humongous and infeasible number. And because of this, only some nodes even bother to compete in this block creation process. And this is what is known as Bitcoin mining, basically the process of repeatedly trying and solving these hash puzzles. And we call these nodes miners. And because of how capital intensive this process is, this goes back to what I said at the beginning, that even though technically anybody can be a miner, there's been a lot of concentration of power or concentration of participation in the mining ecosystem. So that's the first property of these proof of work puzzles. The second property is that we want this cost to be parameterizable. It's not a cost that is fixed over all time. And the way that that's accomplished is that all the nodes in the Bitcoin peer-to-peer network will automatically recalculate the target, that is the size of the target space as a fraction of the output space, every 2 weeks. And they do it in such a way that they maintain this invariant, which is that the average time between any 2 successive blocks produced globally in the overall Bitcoin network is about 10 minutes. So let's think about what this means. What this means is that if you're a miner and you've invested a certain fixed amount of hardware into Bitcoin mining, but the overall mining ecosystem is growing. More miners are coming in, or they're deploying faster and faster hardware. That means that over a 2-week period, slightly more blocks are going to be found than expected. And so nodes will automatically readjust the target. And so the amount of work that you have to do to be able to find a block is going to increase. So if you put in a fixed amount of hardware investment, the rate at which you find blocks is actually dependent upon what other miners are doing. So there's a very nice formula to capture this, which is that the probability that any given miner, Alice, is going to win the next block is equivalent to the fraction of global hash power that she controls. Which means that if she has mining hardware that's about 0.1% of total hash power, she will compute roughly 1 in every 1,000 blocks. So why does this readjustment happen? Why do we want to maintain this 10-minute invariant? Well, the reason is simple. If blocks were to come very close together, then there would be a lot of inefficiency, and we would lose the optimization benefits of being able to put a lot of transactions, as it currently stands, several hundred transactions in a single block. If you went down from 10 minutes to 5 minutes, it would probably be okay. And there are a lot of discussions about if we're doing an altcoin now, what is the block latency that we should have? But everybody agrees that the block latency should be a fixed amount. It cannot be allowed to go down without limit. And that's why you have this automatic target recalculation property. Now, because of the way that this cost function and proof of work is set up, it allows us to reformulate our security assumption. Here's where we finally depart from the leap of faith that I asked you to take several slides ago. Instead of saying that somehow the majority of nodes are honest, in a context where nodes don't even have identities and not being clear about what that means, we can now state crisply that a lot of attacks on Bitcoin are infeasible if the majority of miners weighted by hash power are following the protocol or are honest. And the reason for that is if a majority of miners weighted by hash power are honest, because of this competition for proposing the next block, this will automatically ensure that there is at least a 50% chance that the next block to be proposed at any point is coming from an honest node instead of a malicious one. Let's now look at the consequences of the fact that solving hash puzzles is probabilistic. Why is it probabilistic? Because nobody can predict which nonce is going to result in solving the hash puzzle. The only way to do it is to try nonces one by one and hope that one succeeds, right? And so this process is called mathematically Bernoulli trials. I won't go into detail on that, but you can look it up. But typically nodes try so many nonces that a discrete probability process called Bernoulli trials can be well approximated by a continuous probability process called a Poisson process. And the end result of all of that is that the distribution, the probability density function of the time to find the next block by any node in the network globally looks something like this. It's called an exponential distribution, but really the upshot is that there is some small probability that if a block has been found now, the next block is going to be found very soon or within a few seconds or within a minute. And there's also some small probability that it will take a long time, maybe an hour, to find the next block. But overall, the network automatically adjusts the difficulty so that the interblock time is maintained at an average long term of 10 minutes. Right. So this is a graph that shows how frequently blocks are going to be created by the entire network, not caring about which miner this is coming from. If you're a miner specifically interested in how quickly you're finding blocks, what does this probability density function look like? Well, it's going to have the same shape, but it's just going to have a different scale on the x-axis. Again, it can be represented by a nice equation. For a specific miner, the mean time to find a block, given that you've just found a block, is going to be 10 minutes divided by the fraction of hash power that you control. So again, if you have 0.1% of the total network hash power, you're going to find blocks once every 10,000 minutes, which is several days. And so not only is your mean time between blocks going to be very high, the variance of the time between blocks found by you is also going to be very high. And this has some important consequences that we're going to be looking at in later lectures. So now let's turn to the third important probability of this proof of work function, which is that it's actually trivial to verify that a node has computed proof of work correctly. What does that mean? Even if it takes a node on average 10 to the 20 tries to find a nonce that succeeds in finding the right property of the hash function, that nonce must be published as part of the block, so it's trivial for any other node to look at the block contents, hash them all together, and verify that the output is less than the target. So this is an important property because, once again, it allows you to get rid of centralization. You don't need any centralized authority verifying that miners are doing their job correctly. Any node or any miner can instantly verify that a block found by another miner satisfies this proof of work property, and thereby they can be sure that this miner put in a lot of computing power into finding that block. Let's now look at mining economics, because we've said that it's quite expensive for miners to be in operation because finding a single block takes computing about 10 to the 20 hashes. At the same time, we've also seen that the block reward is about 25 bitcoins, which is quite a lot of money. So it really boils down to an economics question of whether or not it's profitable for a miner to mine. But we can write down a simple equation that represents what the inputs into this decision are. Fundamentally, the mining reward that the miner gets is in terms of the block reward and transaction fees. The miner asks himself whether that's bigger than or less than their total expenditure, which is the hardware and electricity cost. In fact, Bitcoin mining is so expensive in terms of electricity that that becomes a significant portion of the cost and not just the upfront cost of the hardware. And if the rewards are greater than the costs, then the miner profits. If not, the miner incurs a loss. But there are some complications to this simple equation. The first is that, as you may have noticed, the hardware cost is a fixed cost. It's an upfront cost, whereas the electricity cost is a variable cost that is incurred over time. Another complication is that remember that a reward that the miner gets depends upon the rate at which they find blocks, which depends on not just the power of their hardware, but in fact, more accurately, as the ratio of the power of their hardware as a fraction of the total global hash rate. So that makes it more complicated as well. Another complication is note that the costs that the miner incurs are in terms of dollars or whatever currency that they're using, whereas they're rewarded in terms of bitcoins that are created or bitcoins that are transaction fees. So this equation is really going to depend on what the exchange rate of Bitcoin is doing at any given time. And finally, so far we've assumed that the miner is interested in honestly following the protocol, but it could be the case that the miner could deploy some other mining strategy instead of always finding the next block that extends the longest valid branch. And so this equation doesn't capture all the nuances of the different strategies that the miner can employ. So even though we can write down the simple equation, actually analyzing what it makes sense for miners to do is a complicated game theory problem, and we don't have simple answers to that. Okay, so now we've obtained a pretty good understanding of how Bitcoin achieves decentralization. Let's put it all together now and do a little bit of a recap and understand some high-level points in order to get an even better understanding. So what I'm going to do is I'm going to do a very quick recap of several of the major aspects of Bitcoin that we've learned so far. Let's start from identities. As we've learned, there are no real-world identities required to participate in the Bitcoin protocol. Any user can create a pseudonymous key pair at any moment, any number of them. And when Alice and Bob want to make a transaction, when Alice, for example, wants to know what address Bob wants to get paid at, that's not part of the Bitcoin protocol. That needs to be through some other process, for example, on Bob the merchant's website. So given these pseudonymous key pairs as identities, transactions are basically messages that are broadcast to the Bitcoin peer-to-peer network that are instructions to transfer a coin from one address to another. And a coin really is just a chain of transactions to the extent that we can call anything in Bitcoin an actual coin, and this is something we'll see in much more detail in future lectures. And so this peer-to-peer network that we've looked at, its goal is to propagate all new transactions to all the Bitcoin peer nodes, as well as new blocks to the Bitcoin peer nodes, but it's just going to do sort of the best effort that it can. The real security of the system doesn't come from the perfection of the peer-to-peer network. In fact, the underlying assumption that the network is in fact quite unreliable. But instead, where the security comes from is from the blockchain and the consensus protocol that we spent a lot of time looking at. So what it means for your transaction to be in the blockchain is that it achieves a lot of confirmations. It's not a fixed number. 6 is a commonly used heuristic, but the more confirmations your transaction has received, the more blocks are found that extend the block that contained your transaction, the more certain you can be that your transaction was part of the consensus chain. And now, often there are going to be a variety of orphan blocks. These are blocks that don't make it into the consensus chain. This could represent an invalid transaction or a double spend attempt. It could simply represent the fact that there is latency in the network, and two miners competing to solve this proof of work puzzle simply ended up finding new blocks within just a few seconds of each other. And so both of these blocks were broadcast nearly simultaneously onto the network. So another subtle point here is that if Alice and Bob are two different miners, and Alice has 100 times as much computing power as Bob, what that means is not that Alice will always win the race against Bob to find the next block, but instead, Alice and Bob have a probability ratio of finding the next block in the proportion 100 to 1. So in the long term, Bob will find, on average, 1% of the blocks that Alice does. So those are some of the basics of blockchain and consensus and where the security of the system really comes from. And finally, we looked at hash puzzles and mining. Miners are a special type of nodes that bother to compete in this game of creating new blocks, and they're rewarded for their efforts in terms of bitcoins. And we expect that miners are going to be typically somewhere near the economic equilibrium of the expenditure that they incur in terms of hardware and electricity being somewhere equal to the rewards that they obtain in terms of the new block creation reward and the transaction fee-based rewards. So that's a broad recap of the system. Let me show you in a pointed way how deeply this notion of distributed consensus permeates Bitcoin. Now, in a traditional currency, consensus does come into play in a certain limited extent, which is we have a consensus process around what is the exchange rate of the currency. You can make a rough analogy to consensus in distributed systems. And that is certainly true in Bitcoin as well. We need consensus around the value, the exchange rate of Bitcoin, but consensus goes much deeper in Bitcoin than in other, say, fiat currencies. In fact, you need consensus around state, which is what the blockchain accomplishes, that is a record of which transactions are valid or which transactions have even happened. So even the idea of how many Bitcoins you own is subject to consensus. What it means when I say I own a certain amount or number of Bitcoins is that I mean that the Bitcoin peer-to-peer network, as recorded in the blockchain, considers me, the sum total of all my addresses, to own a certain number of Bitcoins. That is sort of the ultimate nature of truth in Bitcoin. So ownership of Bitcoins is nothing more than other nodes thinking that I own a certain number of Bitcoins. And finally, we need consensus about the rules of the system, because occasionally the rules of the system have to change. There are things called soft forks and hard forks, and we're going to see a little bit more detail of this in later lectures. Now I want to show you another subtle idea, which is very tricky. And it's this very neat idea of bootstrapping that I really found intriguing the first time I encountered it. And so I want to share this with you. So what do I mean by bootstrapping? I mean the tricky interplay between three things in Bitcoin. And what are these three things? Let's start from the notion of security of the blockchain. So obviously we want the blockchain to be secure for Bitcoin to have to be a viable currency. But what is necessary for the blockchain to be secure? What this means is that an adversary shouldn't be able to overwhelm the consensus process, shouldn't be able to create a lot of nodes and take over 50% or more of the new block creation. But when will that be true? What is a prerequisite for that? A prerequisite for that is having a healthy mining ecosystem made up of largely honest protocol-following nodes. So that's a prerequisite for security of the blockchain. But what's a prerequisite for that? When can we be sure that a lot of miners will put a lot of computing power into participating in this hash puzzle solving competition? Well, they're only going to do that if the exchange rate of Bitcoin is pretty high. Why is that? Because they receive rewards denominated in Bitcoins, whereas their expenditure is in dollars. So the more the value of the currency goes up, the more incentivized these miners are going to be. But what ensures a high and stable value of the currency? That can only happen if users in general, people who want to buy Bitcoins, have trust in the security of the blockchain. Because if they believe that the network could be overwhelmed at any moment by an attacker, then Bitcoin is not going to have a lot of value as a currency. So you have this interlocking interdependence between these three things. Right? So the existence of each of these is predicated on the existence of another. So one might flip that around and imagine at the beginning, during Bitcoin's creation, when none of these three things existed, when there were no miners other than what we believe to be Nakamoto himself or whoever the creator was running the mining software, and when Bitcoin didn't have a lot of value as a currency, and when the blockchain was in fact insecure because there was not a lot of mining going on, and so anybody could easily overwhelm this process. How do you go from there, not having any of these three properties, to having all three of them? And that is what I mean by bootstrapping. And it's this very tricky process of how all of these three characteristics were acquired by the Bitcoin system in an interdependent manner with each other. And this was, of course, fueled by a lot of media attention as well, because the more people hear about Bitcoin, the more they're going to get interested in mining. And the more they get interested in mining, the more confidence people will have in the security of the blockchain, because there's now more mining activity going on, and so on and so forth. And so Bitcoin went from having none of these properties to now having, in some large measure, all three of these properties. And that's the interesting bootstrapping feature of Bitcoin. And every new altcoin that wants to succeed also has to somehow solve this problem of pulling itself up by its bootstraps. Okay. Let me leave you now with one final thing, which is that in order to understand consensus and what it's responsible for and what it's not responsible for, a good way to do that is to ask ourselves what would happen if consensus failed and there were in fact a 51% attacker somehow who controls 51% or more of the mining power in the Bitcoin network. So let's see what happens in that case, and let's list a whole variety of things, possible bad things that we think might happen. And let's ask ourselves, which of these are possible for a 51% attacker? First of all, can this attacker steal coins from an existing address? Well, you might guess that the answer is no, because stealing from an existing address is not possible unless you subvert the cryptography. It's not enough to subvert the consensus process. This is a bit tricky. Let's follow through this line of argument. Let's say that this 51% attacker creates an invalid block that contains an invalid transaction that represents stealing bitcoins from an existing address that the attacker doesn't control and transferring them to his own address. Now this attacker can pretend that that's a valid transaction and pretend that that's a valid block and keep building upon this block and even succeed in making that the longest branch, but the other honest nodes are simply not going to accept this invalid block and are going to keep mining based on the last valid block that they found in the network. So what will happen is that there will be what we call a fork in the chain. Now imagine this from the point of view of the attacker trying to spend these invalid coins and send them to some merchant Bob and buy something in exchange. Now Bob will presumably be running a Bitcoin node himself, and that will be an honest node, and that node is going to say, oh, this might be the longest branch, but it's not a valid branch because it contains an invalid transaction because the crypto, the signatures, didn't check out. And so it's going to simply ignore this longest branch because it's an invalid branch. And because of that, subverting consensus is not enough. You have to subvert cryptography to steal coins from an existing address. So we conclude that this attack is not possible for a 51% attacker. By the way, in saying all of this, I should note that this is all somewhat hypothetical, somewhat a thought experiment, because if there were, in fact, actual signs of a 51% attack, what will probably happen is that the developers will notice this and will try to react to it, and will update the Bitcoin software, and we might expect that the rules of the system of the P2P network might change in some form to make this attack more difficult to launch, but we can't quite predict that, so we're working in a simplified model where a 51% attack happens, but other than that, there are no changes or tweaks to the rules of the system. Okay, let's move on. Can the attacker suppress some transactions? Let's say there is some user, say Carol, whom the attacker really doesn't like, and the attacker knows some of Carol's addresses and wants to make sure that no coins belonging to any of those addresses can possibly be spent. Is that possible? Well, let's think about this. The attacker, since he controls the consensus process of the blockchain, can simply refuse to create any new blocks that contain transactions from one of Carol's addresses, and can in fact also refuse to build upon blocks that contain such transactions. And the attacker will be successful at that. However, the attacker cannot prevent these transactions from even being broadcast to the peer-to-peer network, because the peer-to-peer network doesn't depend on the blockchain, doesn't depend on consensus, and we're assuming that the attacker doesn't fully control the network. So the transactions are still going to find a way to reach the majority of nodes. So even if the attacker tries this attack, it will be very clear that that attack is happening because the peer-to-peer network will still receive these transactions. Okay, what about this one? Can the attacker change the block reward? Can the attacker start pretending that the block reward is, instead of 25 bitcoins, 100 bitcoins or something like that? Well, this sort of corresponds to changing the rules of the system, and because of a reasoning similar to what we applied for stealing bitcoins from an existing address, this is also not possible because the attacker doesn't control the copies of the Bitcoin software that all of the honest nodes are running. So that's also not possible. Finally, let's ask ourselves if the attacker can somehow destroy confidence in Bitcoin. Well, let's imagine what would happen if there were a variety of double spend attempts and behavior of not extending the longest valid branch and other such attempted attacks. Then people are going to look at this and decide that Bitcoin is no longer acting as a decentralized ledger that they can trust. And so people will simply lose confidence in the currency, and we might expect that the exchange rate of Bitcoin is going to plummet. In fact, if there is a 51% attacker, and this is known, even if the attacker is not necessarily trying to launch any attacks, it's possible that this might happen. So this we can classify as not only possible, but in fact likely that a 51% attack of any sort will simply destroy confidence in the currency. And this last one is in fact the main practical threat if a 51% attack were ever to materialize. None of these others really, considering the amount of expenditure that the adversary would have to put into attacking Bitcoin and achieving a 51% majority, really makes sense from a financial point of view to try any of these other attacks. Great. So now, hopefully, you've obtained a really good understanding of how decentralization is achieved in Bitcoin, and understood identities, understood transactions, understood the peer-to-peer network, understood the blockchain and consensus, understood hash puzzles and mining. So you should be at a really good point now, and a good launching point for understanding a lot more of the subtle details and nuances of Bitcoin, which we're going to start seeing in the next few lectures. So the next lecture is going to be by Joe Bonneau, where he will address a lot of questions that take off from the point where we've left off in this lecture. The first is, how do we get from consensus to currency? So this is an assumption that I've already made in this lecture. Not only are we solving a distributed consensus problem, but also we're treating the result of distributed consensus as a currency in order to incentivize participants. But a lot of details are missing. What exactly does it mean to be paid in Bitcoin? How does that happen? How are those transactions represented, and so on? We're going to look at that. We're going to look at what else can we do with consensus. I hinted at this a little bit, but it turns out that Bitcoin offers a lot in addition to just doing consensus.
Welcome to the third lecture in our series on Bitcoin. This lecture is going to be all about the mechanics of Bitcoin at a fairly low level. So whereas in the first two lectures we've talked at a relatively high level, in this lecture we're going to be trying to give it to you as real as possible. So look at real data structures, real scripts, try to learn the details and language of Bitcoin in a precise way to set up everything that we want to talk about for the remainder of the course. So in some ways this will be the most challenging lecture because a lot of details are going to be flying at you. It's also one of the most real, where you're really learning the specifics and the quirks that make Bitcoin what it is. So to recap where we left off last time, the Bitcoin consensus mechanism gives us an append-only ledger. So a data structure that we can only write to, and once data is written, it's there forever. And there's a decentralized protocol for establishing consensus about the value of that ledger. And the miners who perform that protocol are validating transactions, so making sure that transactions are well formed, that there aren't double spends, and that this thing can function as a currency. Although it's kind of funny because we assumed that a currency existed to motivate these miners. So in this lecture we'll be looking at the details of how we actually build that currency to make the miners make this whole process happen. All right, so we'll start by looking at transactions in Bitcoin. Transactions are really the fundamental building block which the whole currency is going to be based on. So remember, we have this ledger. The ledger is append only, so as time goes on we just add more and more units to it. We're going to take a simplified model here where instead of having blocks we just have individual transactions being added to the ledger one at a time. So how can we build a currency this way? So the first model you might think of, which is actually a lot of people's mental model for how Bitcoin works that we'll look at first is that you'd have an account-based system. So you can add some transactions that create new coins and credit them to somebody. And then later you can transfer them and you just have a transaction that would say, we're moving 17 coins from Alice to Bob. That will be signed by Alice to authorize the transaction. And that's all the information that would be contained. Now backing this up, there would be some state that says that after Alice received 25 coins in the first transaction and then transferred 17 coins to Bob in the second transaction, Alice would have an account that is left with 8 Bitcoins. So now after that transfer from Alice to Bob, we can add some more transactions to the ledger. We'll say that Bob pays some Bitcoins to Charlie, Charlie pays some coins to Alice. And at this point, each participant, Alice, Bob, and Charlie, has an account with a different value in it, and those values are going to mutate each time we add a new transaction. Now the downside of this system, if we add a new transaction at the bottom here, is that we have to remember what the account balance is for each participant to figure out if this transaction is valid or not. Does Alice have the 15 coins that she's trying to transfer to David here? So sure enough, looking at this just with your naked eye, it's fairly hard to tell to do the mental arithmetic to figure out if Alice has enough money to transfer to David here. And in fact, to figure this out, you'd have to look backwards in time forever to see every transaction affecting Alice and whether or not her net balance at the time that she tries to transfer 15 coins to David is greater than 15 coins. Okay, so to tell if this transaction is valid or not, we have to figure out whether or not Alice has the 15 coins that she's trying to transfer to David. And to figure that out, we might have to look backwards forever to the beginning of time at every transaction that's ever involved Alice. Every time Alice has sent or received coins, we need to find all of those transactions and add them up to see if she really has the 15 coins that she's trying to transfer to David. And of course, we can make this a little bit more efficient with some data structures that track Alice's balance after each transaction, but that's going to require a lot of extra housekeeping besides the blockchain itself. And that's why Bitcoin isn't based on an account-based model like this. Instead, Bitcoin uses a ledger that just keeps track of transactions. So how does that work? So this is a transaction-based ledger, which is very close to Bitcoin. So now transactions explicitly specify a number of inputs and a number of outputs. And transactions also each have a unique identifier. So we'll start with transaction 1, which has no inputs, because this is new currency being created, and an output of 25 coins going to Alice. And again, since this is a transaction where new coins are being created, there's no signature required here. Now, let's say that Alice wants to send some of those coins over to Bob. Well, now she has to explicitly refer to the previous transaction where these coins are coming from. So the input to this transaction will be output index 0 from transaction 1, which we can see from the very previous transaction in the log was a transaction that assigned 25 Bitcoins to Alice. And now there are two outputs of this transaction. One of them is 17 coins to Bob, and one of them is 8 coins to Alice. And of course, this whole thing is signed by Alice so that we know that Alice actually wants to do this transaction. And now you might ask, why does Alice have to send money to herself here? She's taken the 25 coins that were assigned to her in transaction 1. She only wanted to pay 17 to Bob, and she has to have a new output where 8 coins are sent back to herself, possibly to a different key, but to herself. So this is what's called a change address. And the design here is that you always completely consume the output of a previous transaction. So there's no way to say I only need 17 coins from that previous output. You have to say I'm using all 25 coins from the previous output, but since you want to keep some, you just have a second output that sends some of the coins back to yourself, which is called a change address. Now, let's say that we keep going with this system, and now we add a new transaction, and we ask ourselves again, is this new transaction valid? Now it's much easier to look at the blockchain and figure out whether or not this transaction is valid, because we know exactly which input to look at. So we just need to go to transaction 2, output 1, and verify that there's enough money there and that it hasn't been sent already. And of course, we can look back and say, yes, that second output of transaction 2 went to Alice with 8 coins, therefore it's enough to cover the outputs of this transaction. It's a finite backward scan to check for the validity. And we implement this with hash pointers. So again, each transaction has a unique ID. In reality, they're not serial numbers like this, it's the hash of the block. And each transaction actually gets its specific ID as well, which is the hash of the transaction. And now it's basically just following one pointer to figure out whether or not there's enough money to cover the desired outputs in the new transaction. Now conceptually, you could say maybe this isn't that much different than just maintaining a separate data structure which tracked account values for each person. But the nice thing is that now this data structure is embedded within the data in the blockchain itself. So some other things that we can do quite easily here, we can merge value. So let's say there's 2 different transactions that send some money to Bob, 17 coins in transaction 1 and 2 coins in transaction 2. Bob might say, I'd like to have one transaction I can spend later where I have all 19 coins. So this is pretty easy. You just create a new transaction that has 2 inputs now and only 1 output, so all of those coins go to Bob. And you've combined the 2 previous transactions into one that Bob can then spend later. Similarly, we can do joint payments pretty easily. So let's say that Carol and Bob both want to pay David. We can have a transaction with 2 inputs that are actually owned by 2 different people and combine the value and pay all 8 coins to David. And the only extra thing here is that since the 2 outputs that are being claimed here are owned by 2 different people, we're going to need 2 separate signatures, one by Carol and one by Bob. So conceptually, that's really all there is to it, to a Bitcoin transaction. And let's look at what it looks like at the low level. So again, one of the goals of this lecture is going to be to show you the real data structure, the real deal of what Bitcoin looks like. And here it is. Now, this isn't exactly what a Bitcoin transaction looks like. This is a representation of it that is pretty printed. It looks kind of like JSON. In reality, there's a compact binary format that this gets compiled down to that's not human readable, but this is very, very close to the actual low-level transaction. So there's 3 parts. There's some metadata, there's a series of inputs, and a series of outputs. So we'll start with the metadata. So there's some housekeeping information, which is the size of the transaction, the number of inputs, and the number of outputs. Pretty straightforward stuff. There's the hash of the entire transaction, which, as I said, will serve as a unique ID for the transaction to let us do hash pointers. And then there's this funny lock time parameter, which I'll come back to later. The transaction inputs is just an array of inputs that all have the same form. The inputs specify a previous transaction specifically, so they have the hash of the previous transaction or a hash pointer to it, and the index of which output from that transaction you're actually claiming. And then there's a signature. So remember that we have to sign to show that we actually have the ability to claim those previous transaction outputs. And now the outputs have just 2 things. They have a value, so each output can have a different value. The sum of all the outputs has to be less than the sum of all the inputs. And then there's this funny thing that looks like what we want to be the recipient address. So each output is supposed to go to a specific person or to a specific public key. And there is some stuff in there that looks like it's the hash of a public key. But there's also some other stuff that looks like a script. And in fact, it is a script, and we'll talk more about that very soon. Okay, so like we said, each transaction output doesn't just specify a simple public key, it actually specifies a script. So what do I mean by that? What is a script and why do we use scripts? In this section, we're going to talk about what the Bitcoin scripting language is and why script is used instead of simply assigning a public key. Okay, so to understand scripts, I think the easiest way is by an example. And we'll take as an example the most common script in Bitcoin, which is to redeem a previous transaction by signing with the correct public key. So this is what the output address would look like in that case. The output address is really a script. And in this case, the script is going to have 4 instructions. So what happens to this script? Who runs it? How does this script indicate who has the ability to spend these coins? The secret is that the input address is also a script. So that's a bit of script that you combine with the output address. You simply concatenate them. And that gets you one script that has to run successfully in order to claim a Bitcoin. So traditionally, these two scripts are called script sig and script pub key. And that's because in the simplest case, the output script just specifies a public key, and the input script specifies a signature with that public key. When a transaction is being validated, the two scripts get pasted together, they get run, and if the concatenated script can run without any errors, this is considered a valid transaction. So where did this scripting language come from? It doesn't really have a proper name. It's just called Script, or the Bitcoin scripting language, and it was built specifically for Bitcoin. It was probably most inspired by a language called Forth, which is an old stack-based simple programming language. But you don't need to understand Forth to understand Bitcoin scripting. The key design properties here were to have something that was quite simple, quite compact, but yet had support for pretty sophisticated cryptography. So there are special purpose instructions to compute hash functions and to compute signatures and verify signatures. And this is a stack-based language. And you may have never seen a stack-based language before in your life, but I'll explain on the next slide what that means and why that was chosen. So there are a lot of limits here that are important to keep in mind. In particular, there are no loops in the Bitcoin scripting language. Every instruction is executed exactly once in a linear manner. So if you look at a script, just based on the number of instructions in the script, you know exactly how long it might take to run and how much memory it could use. So this is not a Turing-complete language. It doesn't have the ability to compute arbitrarily powerful functions, and this is by design because the miners have to run these scripts, which are submitted by arbitrary participants in the network, so you don't want to give them the power to submit a script that might have an infinite loop or might run forever. And since it's not a Turing-complete language, we don't have the halting problem. You can look at any Bitcoin script and be sure that it's going to terminate within a finite number of steps, which is just the number of instructions that are in that script. Okay, now the fun part. We're going to look at a specific Bitcoin script and exactly how it's executed. This is the same example as before. This is the most common script in Bitcoin. A script where the sender of coins simply specifies the public key of the recipient, and the recipient of the coins, to redeem them, has to specify a signature using that specified public key. So the first two instructions in this script are simply data instructions, like I said, and these are the signature and the public key used to generate that signature. And these were specified by the recipient in that script sig component or the input script. So executing data instructions is easy in a stack-based language. If you see data, you just push it onto the stack. And that's the only interaction with memory that you have in a stack-based programming language. There's no variables, there's only a stack. So the only thing you can do to write data to memory is to push it onto the stack. So after we've pushed those two values onto the stack, we're going to start executing the second half of the script, which was specified by the sender of the coins. So this is the script pub key component of the script. And now we're going to start to actually manipulate some of those values on the stack. So this duplicate instruction, opdup, says simply take the value that's on the top of the stack, pop it off, and then write 2 copies back to the stack. So we're just going to duplicate that public key. The next instruction, hash 160, says take the top value on the stack and compute a cryptographic hash of it. So this top value is going to be converted from the public key into a hash of the public key. Now we're going to do one more push of data onto the stack. And this data, remember, was specified by the sender of the coins. So this is the public key that the sender specified had to be used to generate the signature to redeem these coins. So now at the top of the stack we have two values. We have the hash of the public key as specified by the sender, and the hash of the public key that was actually used by the recipient when trying to claim the coins. And we'll just run this equal verify command, which just says, are the two values at the top of the stack equal? If they aren't, an error is going to be thrown and the script will stop executing. But we'll assume that they are. We'll assume that the recipient of the coins actually did use the correct public key. That instruction will consume those two data items that are at the top of the stack. So now we're left with two data items on the stack, a signature and a public key. And we've already checked that the public key was the right public key that was specified by the sender of these coins. And now we want to check that the signature is actually valid. So this is where the power of the Bitcoin scripting language really comes into play. There's one instruction here that lets you verify a signature. So it's easy to write scripts that do signature verification without calling any special library to check the signatures. That's all built into the Bitcoin scripting language. Now, one thing I haven't told you is what is this actually a signature of? What was the input to the signature function? And it turns out there's only one thing you can sign in Bitcoin, which is an entire transaction. So this check sig instruction is going to verify that the entire transaction was successfully signed. So in just one go, hopefully the check sig instruction will pop those remaining two items off of the stack, check that the signature is valid, and now we've executed every instruction in the script. There's nothing left on the stack. And if we haven't had any errors, the output of this script will be a simple yes. So every Bitcoin script can only produce two outcomes. It can either execute successfully with no errors, in which case the transaction is valid. If there's any error while the script is executing, the whole transaction will be invalid and shouldn't be accepted into the blockchain. So a little bit more about the Bitcoin scripting language. It's very small. There's only room for 256 instructions because each one is given 1 byte. And of those, 15 of them are currently disabled, so you can't use them at all. And 75 of them are reserved, so haven't been assigned any specific meaning yet, but might be instructions that are added later in time. So there's a lot of the basic instructions that you'd expect in any programming language are going to be there. There's basic arithmetic, basic logic like if and then, throwing errors, not throwing errors, returning early. And finally, there are crypto instructions, like I said. So there are hash functions, instructions for signature verification, and there's a special, very important instruction for multi-signature verification. That's called check multi-sig. So this, even more powerful than checking just a single signature with one instruction, Bitcoin actually lets you check multiple signatures with one instruction. So with multi-sig, you specify n public keys, and you specify a parameter t, or a threshold. And for this instruction to execute validly, there have to be at least t signatures, t out of n of those public keys that are valid. So we'll show some examples of what you'd use multi-sig for in a second, but this is quite a powerful primitive that in a compact way in the Bitcoin scripting language, you can express the concept that t out of n of these public keys must sign in order for this transaction to be valid. So there's an important bug here. There's a gotcha, which has been there since the beginning of time, which is that in the original implementation of this, the check multi-sig instruction actually pops an extra data value off the stack and ignores it. So this is just a quirk of the Bitcoin language. It's something that in programming you have to deal with by putting an extra dummy variable onto the stack. And at this point, it's considered a feature in Bitcoin in that it's not going away. The costs of removing it are much higher than the damage it causes. So this is just a fun bug that everybody in the Bitcoin community gets to live with. So, like I've said, we have this whole scripting language that lets us specify, in some sense, arbitrary conditions that must be met in order to spend coins. But as of today, this isn't used very heavily. So if you look at the history of Bitcoin and look at what scripts have actually been used, the vast majority, 99.9%, are exactly the same script, which is in fact the script I showed you in our example of a script execution a script that just specifies one public key and requires a signature for that public key in order to spend the coins. There's a few other things that have some use. So multisig gets used a little bit, and there's a special type of script called pay-to-script hash that I'll talk about in just a minute. But other than that, there hasn't been too much creativity in terms of what scripts people actually use. And one reason for that is that Bitcoin nodes by default have a whitelist of scripts, and they refuse to accept scripts that they consider not standard. This doesn't mean that those scripts can't be used at all, it just makes them harder to use. And I'll talk about exactly what that means a little bit later when we talk about the Bitcoin peer-to-peer network. Okay, so I mentioned that some of the scripts are what we call proof of burn. So proof of burn is actually a script that can never be redeemed. So if you have a proof of burn script, it's provable that those coins have been destroyed. There's no possible way for them to be spent. This is quite simple to implement. You just use this code op-return, which throws an error if it's ever reached. And no matter what values you put before then, that instruction will get executed eventually, in which case this program will crash. The data that comes after op-return is never going to be looked at, so this is an opportunity for people to specify arbitrary data in a script. So what is the point of proof of burn? Well, there's two main things that this gets used for. The first is to write arbitrary data into the blockchain. If for some reason you want to write your name, or if you want to timestamp and prove that you knew some data at a specific time, you can create a very low value Bitcoin transaction that's proof of burn. So you can destroy a very small amount of currency, and in exchange you can write whatever you want into the blockchain, which should be kept around forever. The other example of proof of burn we'll talk about in a later lecture on alternate currencies, but it can be a way to bootstrap an alternative to Bitcoin by forcing people to destroy Bitcoin in order to gain coins in the new system. So one thing that's funny about this is that the sender of coins has to specify the script exactly. So this might be funny if you're a consumer, you're shopping online, you're about to order something, and you say, all right, I'm ready to check out, I'm ready to pay, tell me the address where I should send my coins. And the retailer came back and said, oh, well, we're doing something fancy now. We're using multisig. We're going to ask you to send the coins to some complicated script. You might say, I don't know how to do that, that's too complicated. As a consumer, I just want to send to a very simple address. So in response to that problem, there's a really clever hack in Bitcoin, which is that instead of having the sender specify the entire script, the sender can specify just a hash of the script that is going to be needed to redeem those coins. So this looks like the sender specifying a very simple script, which just hashes the top value on the stack and checks to see if it's equal to the required redemption script. So the receiver of those coins, all they have to do, it looks like, is just specify the right script, and then this transaction will verify. So the basic script is very easy to satisfy here. The receiver just has to specify as a data value the value of the script that whose hash the sender specified. But after this happens, a special second step of validation is going to occur, where that top data value from the stack is going to be reinterpreted as instructions, and then it's going to be executed a second time as a script. So we see there were two stages that happened here. First, there was this traditional script which checked that the redemption script had the right hash, and then the redemption script will be deserialized and run as a script itself, and here's where the actual signature check is going to happen. So this is called pay-to-script hash in Bitcoin as an alternative to the normal mode of operation, which is pay to a public key. And the reason this was so complicated is that this was added to Bitcoin after the fact. This wasn't part of the initial design specification. This is probably the most notable feature that's been added to Bitcoin that wasn't there in the original specification. And it solves a couple of important problems. It removes complexity from the sender, so the recipient can just specify a hash that the sender sends money to. And it actually has a nice efficiency gain, as we'll talk about later, since miners have to track the set of output scripts that haven't been redeemed yet. The output scripts are now as small as possible with pay-to-script hash, because they just specify a hash, and all of the complexity is pushed to the input scripts. So we've just invested the effort to understand Bitcoin scripts a little bit, but I haven't really shown you what's so cool about Bitcoin scripts yet. It turns out you can do quite a lot of neat things that will justify the complexity of having a scripting language instead of just specifying public keys. So one of them is to do an escrow transaction. So this is a classic situation online. Alice and Bob want to do business with each other. Maybe Alice has just won some online auction and is ready to buy some things from Bob. Now Alice wants to pay Bob in Bitcoin for Bob to send some physical goods back to Alice. But we get into this problem where Alice doesn't want to pay until after she's received the goods, but Bob doesn't want to send the goods until after Bob has been paid. So what can we do about that? There's quite a nice solution in Bitcoin that's actually used quite heavily in practice, which is to introduce a third party and do escrow transactions. So how does this work? Well, Alice is going to send the money not directly to Bob, but create a multi-sig transaction that requires 2 of 3 people to sign in order to redeem the coins. And those 3 people are going to be Alice, Bob, and Judy, who's a judge who's going to come into play in case there's any dispute. So Alice will create this transaction for the desired amount with that 2 out of 3 multi-sig between Alice, Bob, and Judy. Alice signs the transaction, redeeming some coins that she owns, and this will get published in the blockchain. So at this point, these coins are held in escrow between Alice, Bob, and Judy, and any 2 of them can specify where the coin should go. So Bob will be satisfied after that happens that he's safe sending the goods over to Alice. So he'll mail them or deliver them physically. Now what we hope happens in the normal case is that Alice and Bob are both honest, in which case the goods arrive on time. They're what Alice was expecting, and she wants to actually release the money from escrow so that Bob can spend it. So if this happens, Alice and Bob can both sign a transaction redeeming the funds from escrow and sending them to Bob. And the great thing here is that Judy never had to get involved at all. There was no dispute, and so Alice and Bob were able to sign, and that represents 2 out of the 3 people required by the multi-sig transaction. So in the normal case, this isn't that much less efficient than Alice just sending Bob the money. It requires just 1 extra transaction on the blockchain. Now, what would have happened if Bob didn't actually send the goods? Or if he tried to send them and they were lost in the mail? Maybe he sent the wrong size. Alice now doesn't want to pay Bob because she thinks that she got cheated and she wants to get her money back. So Alice and Bob are definitely not both going to sign a transaction that releases the money to Bob, but Bob's also not going to sign a transaction that releases the money back to Alice because he may be denying Alice's claim of fraud here. So now we're going to have to get Judy involved. Judy's going to have to decide which of these 2 people was honest, which one doesn't deserve the money. And if Judy decides that Bob cheated, Judy will be willing to sign a transaction along with Alice, sending the money from escrow back to Alice. So Alice and Judy can get together. That's 2 of the 3 required signatures, and Alice can get her money back. And of course, Judy would have the opportunity to rule in the other direction. If Judy thinks that Alice is at fault here and Alice is simply refusing to pay when she should, Judy can sign a transaction with Bob, sending the money to Bob. So Judy essentially has full control here, but the nice thing is that she won't have to be involved unless there's a dispute. Another cool application is what are called green addresses. So the problem here is that Alice wants to pay Bob, and Bob's offline. So Bob can't go and look at the blockchain to see if a transaction that Alice is sending is actually there. Maybe Bob simply doesn't have the time to go and look at the blockchain and wait for the transaction to be confirmed. Remember that normally we want a transaction to be in the blockchain and be confirmed by 6 blocks, which takes up to an hour before we trust that it's really in the blockchain. Or maybe Bob is just in a Faraday cage and doesn't have any connection to the internet at all, so Bob is never going to be able to check the blockchain. This would be the case, say, if Bob is a person selling food on the street. So to solve this problem of being able to send money using Bitcoin without the recipient being able to access the blockchain, we have to introduce another third party, which is the bank. So Alice is going to talk to her bank and say, hey, it's me, Alice. I'm your loyal customer. Here's my card or my identification. And I'd really like to pay Bob here. Could you help me out? And the bank will say, sure, I'm going to deduct some money out of your account and draw up a transaction from one of my green addresses over to Bob. So notice that this money is coming directly from the bank to Bob. Some of the money, of course, in a change address is going back to the bank maybe. But essentially the bank is paying Bob here from a bank-controlled address. That bank-controlled address comes with a guarantee that that money will never be double spent. So as soon as Bob sees that this transaction is signed by the bank, if he trusts the bank, if he trusts the bank's guarantee not to double spend the money, he can accept that that money will eventually be his when it's confirmed in the blockchain. Now notice that this is not a Bitcoin enforced guarantee. This is a real-world guarantee. So Bob has to trust that the bank in the real world is doing a business and cares about their reputation and won't double spend for that reason. And the bank will be able to say, you can look at my history, I've been using this green address for a long time and I've never double spent, therefore I'm very unlikely to do so in the future. Of course, if the bank ever does double spend, trust in this whole system is going to collapse pretty quickly. And in fact, the two most prominent online services that implemented green addresses, which were InstaWallet and Mt. Gox, both ended up collapsing. So for that reason, green addresses aren't used as much in Bitcoin as when they were first proposed. People were really excited and thought this was a great idea and a way to do payments more quickly and without accessing the blockchain. Now people are actually quite nervous about this idea. And they're worried that this puts too much trust in the bank. As a result, this isn't used that much in practice, even though it's a cool protocol. A third example I'd like to show you is a way to do efficient micropayments. So the setup here is that Alice is a customer who wants to pay Bob a low amount of money for some service that she's going to use. So maybe in this case, Bob is really Alice's wireless service provider, and Alice wants to pay a small amount of money for every minute that she talks on her phone. Now you can see why a solution that won't work here is to simply create a Bitcoin transaction every minute that Alice speaks on the phone. That's going to create too many transactions, there will be too many transaction fees, and nobody's happy about that. The simple solution here is to create a new low-value transaction every minute that Alice talks on the phone. So if she talks for 2 hours, you might need over 100 transactions. Now, the problem that you're going to get into in that system is that those transactions might be all very low value, and the transaction fees might really kill you. So if the value of each one of these transactions is on the order of what the transaction fees are, you're going to be paying quite a high cost to do this. So what we would like is if you can combine all these small payments into one big payment at the end. And there's actually a neat way to do this with serial micropayments. So how is this going to work? So we start with a multi-sig transaction that pays the maximum amount Alice would ever need to spend to a multi-sig transaction requiring both Alice and Bob to sign to release the coins. Now, after the first minute that Alice has used the service, or the first time Alice needs to make a micropayment, she signs a transaction spending those coins that were sent to the multi-sig address, sending one coin to Bob and returning the rest to Alice. After the next minute of using the service, Alice signs another transaction, and this time she's paying 2 coins to Bob and sending the rest to herself. And notice that these are just signed by Alice. They haven't been signed by Bob yet. Alice is going to keep sending these transactions to Bob every minute that she uses the service. Notice that these aren't getting published in the blockchain, they're just getting sent from Alice to Bob. Eventually, Alice is going to finish using the service, in which case she'll tell Bob, I'm done, you can cut off the service, I'm not going to pay you anymore. And Bob's going to say, great, I'll disconnect your service, and I'm going to take that last transaction that you sent me, and I'm also going to sign that and publish that to the blockchain. So since each transaction was paying Bob a little bit more and Alice a little bit less, whatever the final one is what Bob is going to choose to actually redeem, paying him for the service that he was provided and giving the rest of the money back to Alice. And the great thing is that all those transactions that Alice signed along the way won't make it to the blockchain. Bob doesn't have to sign them. They'll just get discarded. So technically, all of these transactions are double spends. So unlike the case with green addresses, where we were specifically trying to avoid double spends with a strong guarantee, with this micropayment protocol, we're actually generating a huge amount of potential double spends. Although in practice, if both parties are operating normally, Bob will never sign any transaction but the last one, in which case the blockchain won't actually see any attempt at a double spend. Now there's one more detail here, if you stop and think for a second, which is somewhat tricky to deal with. What if Bob never signs the last transaction? He may just say, I'm happy to let the coins sit there in escrow forever, in which case maybe the coins won't move, but Alice will be out the full value that she paid at the beginning. So there's a very clever way to avoid this problem using a feature that I described earlier but haven't explained yet, which I'll need to introduce now. And that feature is called lock time. So to avoid this problem, before the micropayment protocol can even start, Alice and Bob will both sign a transaction which refunds all of Alice's money back to her, but is locked until some time in the future. So before Alice signs the first transaction paying for the first minute of service, she's going to want to get this refund transaction from Bob and be able to hold that in her hand, and know that if she makes it to time t and Bob hasn't signed any of the small transactions that Alice has sent, Alice can publish this transaction which refunds all of the money directly to her. So what does it mean when I said it's locked until time t? How do we do that? Well, you'll remember when we looked at the metadata in Bitcoin transactions that there was this lock time parameter, which I had left unexplained. It's quite simple, actually. If you specify any value other than 0 for the lock time, that tells miners, don't publish this transaction until this point in time. The transaction is invalid and can't be published until either a specific block number or a specific point in time based on the timestamps that are being put into blocks. So this is a way of preparing a transaction that can only be spent in the future if something else doesn't happen. And it works quite nicely in that micropayments protocol as a safety valve for Alice to know that if Bob never signs, eventually she'll be able to get her money back. So hopefully those examples have shown you that you can do some pretty neat stuff with Bitcoin scripts. Those are just 3 examples that are the most practical and simple to explain, but there are a lot of other things that people have looked into doing. One of them is multiplayer lotteries, which is a very complicated multi-step protocol with a lot of transactions with different lock times. There are escrows in case people cheat, but you can actually run a fair multi-party lottery over Bitcoin using just the scripting language, which is really neat. There are other things, like you can pay someone if they know the pre-image of a hash, so you can try to pay somebody to do some brute force work for you. And there are a couple of neat protocols for different people to get their coins together and mix them so that it's harder to trace who owns which coin. And we'll talk about that a lot more in our lecture on anonymity. So the general term for contracts like this is smart contracts, which means that the contracts actually have some technical enforcement of something that used to be enforced through things like laws or courts of arbitration. So it's a really cool feature of Bitcoin that we can use scripts and we can use the miners and we can use transaction validation to enforce things like escrow or the micropayment protocol. And you don't have to rely on any centralized authority to actually enforce these contracts. Now the whole field of smart contracts goes quite deep. There's a lot more smart contracts people would like to apply, a lot of which you unfortunately can't build with the Bitcoin script today. So the Bitcoin script is fairly limited in the types of things that you can address. There's a lot of smart contracts people wish they could build that either are impossible or nobody has come up with a way to do it yet. But you can do quite a few interesting smart contracts with the Bitcoin script. So now let's talk about how Bitcoin blocks get put together. So we've been talking about the blockchain and the fact that transactions are actually grouped by blocks, but everything in this lecture so far we've been talking about just individual transactions getting published. So why do we group transactions together into blocks? Well, a couple reasons. One is that creates a nice single unit of work for miners that's bigger than the individual transaction size. So if the miners had to do work and do hashing and add metadata for every transaction in the system, that would provide too much overhead. It also makes the hash chain of blocks shorter because we only need one block for a large number of transactions. And that's going to make it easier for us to verify the blockchain data structure. So what does the blockchain data structure look like? It's a pretty clever combination of two different hash-based data structures. So on the top here, we have a hash chain of blocks. Each one has a block header and then a pointer to some transaction data, as well as a pointer to the previous block in the sequence. And remember, these are hash pointers. And then we have a tree of all of the transactions that are included in each block. So this is a hash tree, or what's called a Merkle tree, which commits to all of the transactions in the block in quite an efficient way. So it's easy to provide just the path through the tree, which will be logarithmic in size, to prove that that transaction is included in a specific block. So that's the high-level idea behind a block. What does it look like in practice at the low level? So we'll do another deep dive into the actual data here. So this is what a Bitcoin block looks like. There's what's called the block header, which has all of the metadata for that block. And then there's that Merkle tree of transactions. So basically a long list of transactions. All of the hashes are arranged in this tree structure, which gives you the ability to efficiently prove which transactions are included in a block. The most important part, of course, is the header, which mostly has information related to the mining puzzle, which was talked about in the lecture on consensus, and we'll revisit in the lecture on mining. But recall that the most important thing here is that the hash of the block header has to start with a large number of zeros for the block to be valid. And then there's some other data to make that happen. There's a nonce that miners can change. There's a timestamp. There's a indication of how difficult this block was to find. That's all stored in the header. And the important thing is that the header is the only thing that's hashed during mining. So to verify that chain of blocks, all you need to do is look at the headers. And the only transaction data that's included in the header is that one root of the transaction tree. So that's this Merkle root parameter. The other thing that's interesting about blocks is that they have one special transaction in the Merkle tree, which is unlike all the other transactions we looked at before. And this is the coin-based transaction. So this is where the creation of new coins in Bitcoin happens. It mostly looks like a normal transaction with a few exceptions. So the value of this transaction is going to be equal to currently a little over 25 Bitcoins. As we discussed, this is a flat mining reward, which is set by the system and which is halving every 4 years. In practice, it will be a little bit more than 25 Bitcoin because it also gets to include the transaction fees collected from every transaction included in the block. So the pointer to the output transaction that this Coinbase transaction is receiving is a null pointer. It's a hash of all zeros. And this is an indication that since this is the creation of new coins, there is no antecedent. There's no previous transaction that's being consumed to create these coins. And there's also this special Coinbase parameter. And the Coinbase parameter is completely arbitrary. The miners can put whatever they want in there. So famously, in the very first block ever mined in Bitcoin, the Coinbase parameter had a quote from the newspaper. It had a quote from the Times of London describing a story involving the Chancellor bailing out banks, which was both a political commentary on the motivation for starting Bitcoin and served as a commitment that Bitcoin, the first block, was obviously mined after this newspaper came out. But since then, miners are free to put whatever they want in the Coinbase parameter. It's been used as a place to put some arbitrary data for different reasons, to signal support by miners for different new features, but there's no actual limits on what miners can put in there. So with both the block format and the transaction format that we described earlier, the best way to learn it is to just see for yourself. So there's a lot of websites that make this data accessible. This is a screenshot from blockchain.info, which I found very helpful myself in understanding and exploring what's going on at a low level in Bitcoin. There are a lot of other websites that do a great job of making this information accessible. So you can look at the graph of transactions, see which transactions redeem which other transactions, look for transactions with complicated scripts. You can look at the block structure and see how blocks refer to other blocks. It's all available online because, again, the Bitcoin is a public data structure, so a lot of different people have put very pretty wrappers around this to explore it graphically. So we've been talking about the ability for participants to publish a transaction and get it into the blockchain as if this happens by magic. Of course, it doesn't happen by magic in the real world. It happens through the Bitcoin network. So what is a Bitcoin network? It's a peer-to-peer network, so it inherits a lot of ideas from peer-to-peer networks that have been proposed for all sorts of other purposes. It's a peer-to-peer network where all nodes are equal. There's no hierarchy, there's no centralized special nodes, no master nodes. Every node on Bitcoin is an equal peer. It runs over TCP, it has a random topology, so there's random nodes are paired with random other nodes. And new nodes can come in any time. So you can download the Bitcoin client today, you can spin your computer up as a node, and you'll be a participating Bitcoin node with equal rights and capabilities as every other node on the Bitcoin network. Now the network is very dynamic, it changes over time, nodes are coming and going all the time, although there's actually no explicit way to leave the network. Instead, if you don't hear from a node for a while, 3 hours is the amount that's hard-coded into the common clients. People eventually start to forget you, so it gracefully handles nodes going offline. So what does that mean that you can simply join the Bitcoin peer-to-peer network at any time? Well, if this is a picture of the network at one moment in time, obviously scaled down quite a bit with just 7 nodes, but this is a picture of what it might look like, 7 nodes with all random connections to each other. And notice that the numbers are scattered around here because there's no geographic topology here. Networks connect to other nodes in a random fashion by design. Now, if you launch a new node and say you want to join the network, you start with a simple message to one node that you know about. So all you need to know is how to get to one node that's already on the network. This is usually called your seed node, and there's a few different ways you can look up lists of seed nodes to try connecting to. But you find your seed node, and you send a special message saying, tell me all the peers that you have. Tell me the addresses of all the other nodes in the network that you know about. And that node will respond and say, well, I'm paired with nodes 1 and 7, you can try them. And then you might go talk to 1 and 7 and say, hey, tell me everybody on the network that you know about. And they'll send you the nodes that they know about, and you can iterate as many times as you want until you have a list of peers to make connections with. And then you can choose which ones to peer with, and you'll be a fully functioning member of the Bitcoin network. And again, there's a few steps of randomness here, so depending on which seed node you used or which of the peers of the seed node you decided to go and talk to, you'll end up with a random set of nodes that you're connected to, but that's perfectly fine. So now that you're a member of the network, what is the network good for? Well, the network maintains the blockchain, so if you want to publish a transaction, you want to get the entire network to hear about it. And there's a simple flooding algorithm to make this happen. So let's say that node 4 here hears about a new transaction. So Alice wants to pay Bob some money. Alice creates a Bitcoin transaction and submits it to node 4. Or maybe her wallet software or her exchange does that on her behalf. But somehow this transaction gets to node 4. Now node 4 says, great, I've got a new transaction. Alice wants to pay Bob. Let's tell everybody about it. Sometimes this is called a gossip protocol, because it's very simple. If you have news, you try to tell as many people as you can, and they try to tell as many people as they can, much like people gossiping in the real world. Great, so node 4 is going to talk to its neighbors, node 3 and node 2. and say, hey, check out this new transaction. Alice wants to pay Bob. And those nodes will add it to their own pool of pending transactions. So each node maintains a list of all the transactions they've heard about that haven't been put into the blockchain yet. And then they can decide to forward that onto other nodes. So 3 is going to talk to its neighbors and say, new transaction for you, Alice wants to pay Bob. That'll end up in their transaction pools and so on. And we want to make sure that this process doesn't go on forever. So let's say that node 2 comes along later and tries to tell node 7, hey, new transaction, Alice wants to pay Bob. Node 7 is going to say, that's all right, node 2, I've already heard about that. I already got it in my memory pool. I don't need to forward it further. So eventually this thing has to stop because every node will have heard about the new transaction and they won't forward it anymore. And remember, every transaction is identified uniquely by its hash. So each node can tell they've seen that hash before and that they don't need to keep forwarding that transaction, so it won't loop around the network forever. So how do nodes decide when they hear about a new transaction whether or not they should propagate it? The most important thing they do is they check to see, given their view of the blockchain, whether or not this transaction is valid. So they do all the transaction validation we talked about earlier. They run the script, they see that the script checks out, they see that the coins that are being redeemed here haven't already been spent. And if all of that checks out, then this looks like a valid transaction that they should try to relay. With a couple of other caveats, by default, nodes won't relay the transaction if it's a non-standard script. If the script has any weird features, if it doesn't match a fairly simple whitelist of scripts that nodes know about, even though it's a valid transaction, the nodes won't relay it. They'll also make sure that they haven't seen the transaction before. That's that condition to avoid infinite loops. And there's another property, which is that they won't relay the transaction if it looks like a double spend. So if they've seen a transaction where Alice tries to send some specific coins to Bob, and then later they see a second transaction where Alice tries to send those same coins to Charlie, the node shouldn't relay the second transaction. Even though either transaction could be valid because those coins still haven't been spent, they'll only relay the first one they hear. And that's an extra guard against double spending. But it's important to keep in mind that all of these checks are just sanity checks. So well-behaving nodes all implement these to try to keep the network healthy and running properly. But there's no rule that says that nodes have to follow these specific steps. So since it's a peer-to-peer network and anybody can join, there's always the possibility of a node not following this exact protocol, forwarding double spends, forwarding transactions that aren't standard, forwarding transactions that aren't valid. And that's why it's important that every node do the checking for itself. So it's possible that nodes will end up with a different view of the pending transaction pool based on what they've seen. So let's go back to this example where node 4 originally relayed a transaction where Alice was trying to pay Bob. And let's say that this transaction hasn't yet flooded to the entire network, and before it gets to everybody, node 1 is going to announce a new transaction and say, hey, I just heard Alice is trying to pay Charlie. Now from node 1's perspective, this is a valid transaction, and they haven't seen the other transaction where Alice is trying to pay Bob. So node 1 is going to implement the protocol normally and is going to tell all of her neighbors about it. Now the neighbors that haven't heard the conflicting transaction yet will add it to their transaction pool. Whereas other neighbors like node 6 in this example, they've already received a transaction where Alice is trying to pay Bob. So node 6 is going to say, I don't want to hold 2 conflicting transactions in my pool. I'll just keep the one I already have. The network may end up in a divided state here, where different nodes have a different view of what the pending transaction pool is. But that's fine, these transactions haven't been published in the blockchain yet, so this is just a temporary state where nodes disagree on which transaction should be put into the next block. In practice, this is a race condition. If nodes have a different perspective on which transactions are pending or which blocks have been accepted, that's okay in a temporary state, and eventually they'll sort it out. So in the case of transactions, if different nodes have a different view of the pending transaction pool, depending on who mines the next block, they'll essentially break the tie or the race condition and decide which of those 2 pending transactions should end up being put permanently into a block. And once one of those two transactions has been put into a block, other nodes will see that the transaction that they're holding onto in their pool is now never going to make it into a block because it would be a double spend, and they'll just drop it. So if the transaction where Alice tried to pay Bob successfully makes it into a block first, the nodes who heard the transaction where Alice tried to pay Charlie will just say, that's not a valid transaction anymore, so I can forget it. So the default behavior is for nodes to just hang on to whatever they hear first, which means that network position matters. If two conflicting transactions or two conflicting blocks get announced at two different positions in the network, they'll both flood in opposite directions, and the nodes which end up with one transaction or the other will depend on which side of the network they started out closer to. Of course, this assumes that every miner implements this logic where they keep whatever they hear first, but there's no central authority enforcing this. So every node is free to do whatever logic they want. So if for some reason, if any node wants to, they can choose to implement any other logic they want for choosing which blocks or which transactions to forward. We'll talk about that more in our lecture on mining, why miners might want to implement some different logic other than the default. Now, I've been talking mostly about transactions here. The logic for announcing new blocks whenever miners find a new block is almost exactly the same as propagating a new transaction. So the same algorithm is used to announce new blocks around the network. It's the same flooding algorithm, the same gossip process. And in this case, instead of verifying that the transaction is valid by running a script, the nodes are going to verify that the new block is valid by computing the hash and making sure that it starts with a sufficient number of zeros to meet the difficulty target. Now, validating a block is also much more in-depth, because in addition to validating the header and seeing that the hash value is correct, nodes are asked to validate every transaction included in the block to make sure that the block contains only valid new transactions. And the other check, which is this really important critical part that makes Bitcoin consensus what it is that nodes shouldn't forward a block unless it builds on their perspective of the current longest chain. So they have a view of the blockchain, and they should only forward new blocks if they come at the very end of the chain, not at some earlier point. And this avoids forks building up. So just like with transactions, nodes can implement different logic if they want. They're free to relay blocks that aren't valid, or to relay blocks that build off of an earlier point in the blockchain. So some nodes may be trying to relay a block that doesn't extend the current longest chain, that actually builds a fork. And that's okay, the protocol is designed to withstand that. So how long does this flooding algorithm actually take? How much latency is imposed here? This is a graph showing the average time for new blocks to propagate to every node in the network. And the three lines show the 25th, the 50th, and the 75th percentile of how long it takes for a new block to reach every node in the network. And if you look at the 75th percentile there for some of the larger blocks, and this is heavily dependent on size because of bandwidth constraints that some nodes have, you'll see that the average propagation time is over 30 seconds. So this shows that this isn't a particularly efficient protocol. On the internet, 30 seconds is a pretty long time for people to hear about something. The reason it takes so long is because the protocol is not very efficient. It wasn't designed to be efficient, it was designed to be simple and to have no structure so that every node is equal and they can come and go at every time. And as a result, the topology may not be optimized for fast communication. A block may need to go through many nodes before it reaches some of the most distant nodes in the network. Whereas if you design the network top-down for efficiency, you would design it to make sure that the path between any two nodes was very short. For Bitcoin, it's more important to have a decentralized structure where all nodes are equal, even if that means that the propagation time can be over 30 seconds in some cases. So how big is a Bitcoin network? Well, there's no official statistics anywhere because, again, there's no central authority overseeing it. It's simply whatever the nodes participating, they are the Bitcoin network. So it's impossible to measure exactly, and it's changing all the time. But a number of researchers have looked into this and tried to come up with estimates. On the high end, some researchers have said that over 1 million IP addresses in a given month will at some point be running the Bitcoin protocol and acting at least temporarily as a Bitcoin node. But if you look at full nodes that are actually permanently connected and are fully validating every transaction they hear and running the full protocol, it's only about 5 or 10,000, which may be a surprisingly low number. And in fact, that number may be dropping. There's no evidence that the number of fully validating nodes is going up, and there's some concern that the number of fully validating nodes is actually going down. So to be a fully validating node, you want to stay permanently connected so that you hear about all data. The longer you're offline, the more catch-up you're going to have to do to hear about all the transactions you missed. And you're going to have to store the entire blockchain. You'll also need a pretty active network connection so that you can hear every new transaction and forward it to your peers. So you can see the growth over time here. And currently it takes about 20 gigabytes to store the entire blockchain, which isn't too bad. If you have a few years old PC with an active network connection, you have what it takes to be a fully validating node. Although you basically need to dedicate that machine to doing that and not much else. Fully validating nodes maintain the entire set of unspent transaction outputs. So every coin that's available to be spent, and remember, those are just unspent output transactions, ideally you'd like to store this in RAM so that when you hear a new proposed transaction on the network, you can quickly check the transaction that it's attempting to claim, run the script, and see if the signature is valid. So currently there are about 12 million unspent transactions, and that's out of 44 million transactions that have ever been proposed. So fortunately, that's still small enough to fit in less than a gigabyte of RAM in an efficient data structure, so that if you're running a fully validating node, every time you hear about a new transaction, you can quickly check, run the redemption script, and see that this is a valid transaction that you should put in your pending transaction pool. So in contrast to being a fully validating node, there are lightweight nodes, also called thin clients or simple payment verification clients. This is actually the vast majority of nodes on the Bitcoin network. And the difference here is that these nodes aren't attempting to store the entire blockchain. They only store the pieces that they need to verify some specific transactions that they care about. So for example, if you run a wallet, your wallet might want to be a simple payment verification node. And if somebody sends money to you, you'll act as a node. You'll download the bits of the blockchain that you need to verify that the person sending you the money actually owned it and that the transaction sending it to you actually gets included in the blockchain, but you won't care about the thousands of other transactions going on that don't affect you. Now, an SPV client like this won't have the full security level of being a fully validating node. And the reason is that when they hear a new block, the only thing they can check is the block header. They can check to see that the block was difficult to mine, but they can't check to see that every transaction included in that block is actually valid because they don't have the entire previous blockchain. They don't know the entire unspent transaction output set. They can only validate the transactions that actually affect them. So they're essentially trusting the fully validating nodes to have validated all the other transactions that are out there. So this isn't a bad security trade-off. You're assuming there are fully validating nodes out there that are doing the hard work, and that if miners went through the trouble to mine this block, which is a really expensive process, they probably also did some validation to make sure that this block wouldn't be rejected. And the cost savings of being an SPV node are huge. It's about 1,000 times smaller to just store block headers than to store all of the previous transactions. So instead of storing about 20 gigabytes of data, you're down to about 20 megabytes, which is something that almost anybody on a PC or even on a phone can store and act as a limited node in the Bitcoin network. So finally, we'll talk about some built-in limitations to the Bitcoin protocol and why it's challenging to actually improve them. There are a lot of hard-coded constants that are implemented into the Bitcoin protocol, which were chosen when Bitcoin was proposed in 2009, before we really had any idea that it might grow into this globally important currency. So the most important limits are probably the limits on the average time per block, the size of blocks, the number of signature operations in a block, and the divisibility of the currency. The limitations on the total number of bitcoins in existence, as well as the structure of the mining rewards, are very likely to never be changed because the economic implications of changing them are too great. Miners have invested a lot of real-world resources into becoming miners, assuming that Bitcoin rewards would take a certain shape and that the limited supply of Bitcoins would remain the way it's been planned. So if you change that, that would have large financial implications for people. So for that reason, the community has basically agreed that those values, whether or not they were wisely chosen, we're basically stuck with. Some other changes you'd like to make seem like they would make everybody better off. Things about Bitcoin that just weren't quite properly designed at the beginning, but are also hard to change. The main aspect of Bitcoin that people are worried about and would probably like to change if they had time to design it over again are limits that affect the throughput of the system. How many transactions can the Bitcoin network process per second? So this limitation comes from the hard-coded limit on the size of blocks. Each block is limited to 1,000,000 bytes. And each transaction has to be at least 250 bytes. So if you divide through and the fact that blocks are found every 10 minutes, you're left with about 7 transactions per second, which is all that the Bitcoin network can handle. And it seems like tweaking those numbers would be very easy. It's just one constant in a file somewhere that you'd have to change. It would actually be very hard to change this in practice for reasons that will become clear in a few seconds. So how does 7 transactions per second compare? Well, if you went down to the offices of Visa and told them I'm proposing a new payment system that can handle 7 transactions per second, they would probably tell you, that's terrible, and then they would laugh and throw you out the door. They've been working for a long time to build a payment network that goes way bigger than this. So it's said that Visa handles on average about 2,000 transactions per second around the world. And on the busiest times, so think the Saturday before Christmas when everybody's out shopping and swiping a credit card, the Visa network can handle about 10,000 transactions per second. And other payment card networks are similarly big. You can also look at PayPal, which is not as big or as old as Visa, but even PayPal can handle 100 transactions per second at peak times, so an order of magnitude more than Bitcoin. Another limitation that people are worried about in the long term is that the cryptography in Bitcoin is fixed. There's only a couple of hash algorithms, and there's only one signature algorithm, which is elliptic curve DSA, over a specific elliptic curve called SEC P256. And there's some concern that over the lifetime of Bitcoin, which people would like to be for a long time, this algorithm might be broken. Cryptographers might come up with a clever new attack that we haven't foreseen, which makes this an insecure algorithm. And the same is true of the hash functions. Hash functions in the last decade have actually seen steady progress in cryptanalysis, with SHA-1, which is included in Bitcoin, already having some known cryptographic weaknesses. So to change this, we would have to extend the Bitcoin scripting language to support new cryptographic algorithms. So what would it look like to make a change like this, where we just said, we had a problem in Bitcoin, we're going to release a new version of the software, and everybody is going to have to switch? This is what we would call a hard forking change. So in practice, it's impossible to assume that every node would upgrade. Some nodes in the network would fail to get the new software or fail to get it in time. And what would be the implications of that? Well, let's take a look at a network here where most of the nodes have upgraded, but there are a few that haven't. And now let's say one of the new nodes says, hey, I found this nifty, great new block. Maybe it has some new signature algorithm in one of the transactions using the new features that we've added to Bitcoin. So block 4 has found this and says, okay, I'm going to update and say that's now the newest block. So I'm at block index 24. The rest of the network is at 23. But I'm going to propagate that to all of my peers using the normal block flooding algorithm. So node 4 is going to send block 24 out to its neighbors, nodes 3 and 2. Node 3 is going to get it and say, great, I got that one. I'll update my version of the blockchain to have that as the newest block. Whereas node 2 is going to say, that's crazy. You have some operation code that's disabled or reserved. I have to reject this block. I don't understand it. I can't accept it. And similarly, when it gets over to node 6 is also going to say, nope, I can't accept that block either. And now you're going to end up in a state where the new nodes have one picture of the blockchain, and the old nodes have all refused to accept this latest block. So the new nodes will go off and work on a version of the blockchain, including this new block with the new fancy feature. And the old nodes will all be stuck on an old version of the blockchain. And unfortunately, they're never going to catch up, because until they upgrade their software, they'll keep rejecting all of the blocks that are proposed by the nodes in the network that have upgraded to the new version of the protocol. So the reason it's called a hard fork is that the blockchain will split. Every node in the network will be on one side of it based on which version of the protocol it's running, and they'll never join together again. And this is considered unacceptable by the community, that old nodes would effectively be cut out of the Bitcoin network if they don't upgrade their software. So by contrast, there's an approach called soft forking, which tries to avoid creating a permanent fork like this. The observation is that we can add new features to the Bitcoin protocol if they only restrict the set of valid transactions or the set of valid blocks. Because we want to avoid this hard fork situation, we can try to add new features in a way that will cause only a soft fork. So the key to making this happen is that the new features can only make validation rules stricter. They can only limit the set of blocks or the set of transactions that are considered valid. So the new nodes in the network will be enforcing some new, tighter set of rules. So we're relying on enough nodes switching to the new version of the protocol that they'll be able to enforce the new rules, knowing that the old nodes won't be able to enforce the new rules because they haven't heard of them yet. There is a risk here, which is that old nodes might be mining an invalid block because they include some transaction which used to be valid, but according to the new, more strict rules, is not valid anymore. So that could be bad. Those nodes could waste a lot of time mining a block that the new nodes will reject. But when they try to announce that new block, the new nodes will reject it. The old nodes will at least figure out that for some reason, even though I don't understand the reason, the rest of the network has rejected my new block. Therefore, I should move on to the version of the blockchain that all of my peers have, and it won't be a hard fork. They'll have a temporary fork by virtue of the new block they tried to mine that was rejected by the network, but they'll recover and get back onto the main chain. So the classic example of a change that was made via a soft fork was pay to script hash, which we introduced earlier in the section discussing the scripting language. So the view of pay to script hash from old nodes, and again, pay to script hash was not present in the first version of the Bitcoin protocol, they see this script as really simple. All it's doing is hashing this one data value and checking to see if it's equal to the value specified in the output script. The old nodes never do that second step of verification in pay to script hash, where they then check to see that that value before being hashed runs as a valid script. So what could we possibly add with a soft fork? Pay to script hash was successful. It's also possible that new cryptographic schemes could be added by a soft fork, or that we could add some extra metadata in blocks that had some meaning. And the place you'd add this is in the Coinbase parameter. So today, any value is accepted in the Coinbase parameter, but we could in the future say that the Coinbase has to have some specific example. One idea that's been proposed is that in each new block, Coinbase contains a Merkle root of the entire set of unspent transactions. It would only result in a soft fork because old nodes might mine a block that didn't have the required new Coinbase parameter that got rejected by the network, but they would catch up and join the main chain that the network is mining. Other changes might require a hard fork. That would be if we wanted to add new opcodes to Bitcoin, change the limits on block or transaction size, or do a lot of bug fixes. So for example, the bug I showed earlier, where the multisig instruction pops an extra value off the stack, that would actually require a hard fork. And that's the reason why, even though it's an annoying bug that people wish wasn't there anymore, it's much easier to just leave the bug in the protocol and have people work around it, rather than have a hard fork change to Bitcoin. So all of these hard forking changes, even though they would be nice, are very unlikely to happen, at least within the current climate of Bitcoin. But a lot of these ideas have been tested out and proved to be successful in alternative currencies, which start over from scratch, and we'll be talking about those in a lot more detail in our lecture on altcoins. So I spent a lot of time talking about details today. I know this has been a long lecture with a lot of technical detail, very hard to absorb it all at once, so like I said, I would certainly recommend you can go online and see some of this stuff in practice, see what blocks and transactions look like. It took me a couple of times looking at them before I really had a good sense of what was going on, but I think the practical examples do really help. In the next lecture, given all these mechanics we've introduced, we're going to look at the human side of things. Because after all, human beings aren't Bitcoin nodes, and you're never going to run a Bitcoin node in your head. So how do you as a human actually interact with this network to get it to be usable as a currency? How do you find a node to tell about your transaction? How do you get Bitcoins in exchange for cash? How do you store your Bitcoins? So all of these questions are crucial for making a currency that will actually work for people as opposed to just software.
Welcome to Lecture 4, where we'll talk about how we store and use Bitcoins in practice. In section 4.1, we'll talk about the simplest way of storing Bitcoins, and that is simply putting them on a local device. Now, just to review, in order to spend a Bitcoin, you need to know two kinds of things. First of all, you need to know some information that's stored on the public blockchain. You need to know what the identity of the coin is and how much it's worth, for example. And along with that, you also need to know the secret key of the owner of the Bitcoin. Presumably that's you. Now, if you think about it, the first piece of information, being on the public blockchain, you don't need to worry too much about how to store it because you can always get it back when you need it. But the secret signing key is the thing that you'd better keep track of. So in practice, when we talk about how you store your Bitcoins, what we're really talking about is how you store and manage your keys. And that's going to be the main topic when we talk about how to store Bitcoins. So really, this lecture, which we titled How to Store and Use Bitcoins, might as well be called How to Store and Use Secret Keys, because that's really what it's about. Okay, now, when figuring out how we're going to store and manage our keys, there are three goals that we have in mind. The first goal is availability. You want to be sure that you can actually spend your coins when you want.